Okay, our emergent humanity. So I'm very pleased to be here. This is our fourth tutorial with Project Aria, and it's actually our fifth year of externalized Project Aria. And I think, as we say, and hopefully you get to come along to is it a party on Wednesday? It's really the community that is built everything that is worthwhile in Project Aria, built, of course, upon the tools. So hopefully you'll get to see lots of good stuff today on our new generation. But I want to give us a bigger picture, because you're going to get a lot of great technical talks from people, and I'm going to leave that to them. I want to point out that it's really rare in the history of humanity to have an experience of all of humanity seeing their entire species from a different perspective. And just recently I was doing a talk, and we used this Apollo 8 mission to sort of really get this point across. This was a photo of Earthrise that was taken on Christmas Eve from the folks who were on their way to the moon. And they turned around and took this snapshot. And it's kind of fascinating to think of what this really represents in that blue marble, all of humanity. And the perspective, of course, of seeing for the very first time the entire world encapsulated in, what is effectively a very low resolution photo relative to what we're used to today, really profoundly changed the way that people think about themselves on the planet. Because the point is, it's kind of whatever it is, the good, the bad, the potential, it's all inside of that blue marble, as it was. It was incredibly powerful. And it's amazing because here we are, 40 odd years later. Is that right? More than 40 years later, isn't it? My goodness, 70 years later, on the order of. And it's like we are in a position, what is it, Michael? It's like 65, 67. All right, we're going to scratch that from the video. 57 years later, we're still wondering about this photo and what it really means to us. But there's a couple of things that I want to say, which are, let's not forget that everything really still is mostly inside of this blue marble, and that we are yet to really understand it. And what I mean by that is exactly the emergence of humanity. How did it happen? Where's it going? And where's it going with our technologies? So let's begin. Frias Corinthi introduced us to this idea of the 6 degrees of separation, which means that even though there's 8 billion people on the planet today, you're just 6 steps away from interacting with anybody. That is to say that you know somebody who knows somebody, ... that knows, at the very least, Logan in the background here, if not Kevin Bacon. And the reason why that's important is because it means that you're really extremely connectable on this planet. And that was actually true even before the technologies that we have today, like the internet. Of course, the internet has brought us together in an even more obvious way. So even though it's a very big planet with lots of people, in principle, you're just a few degrees away from anybody's mind and what they might have to do to help you with anything that you're thinking about, and you the same for them. Now, on the other hand, your perspective is much more related to this thing called Dunbar's number, which is from Robin Dunbar in only the early 1990s. They did some analysis on the neocortex size of primates, and they were sort of correlating brain size and the capacity to have social networks. And what they found was very interesting, because it was effectively quite related to something that's very intuitive, which is that you have just a few close friends. You have a lot more acquaintances that you might interact with on a direct way, but not as much as day to day. And then you sort of have this growth of the number of people that you interact with, but not necessarily directly, and on, up to about 150 of people that you might really know their names about. And it's a dynamic network, so people will pop into your group of about 150 and they'll pop out again. And overall, that sort of defines your social reach. So, even though if you think about the blanket of these local networks and how they connect via the 6 degrees of freedom, your actual perspective interacting on the planet is kind of defined by Dunbar's number and your local, up to your acquaintances. Like I say, Facebook did a pretty good job of connecting the planet, and sort of by sort of the early 2010s had already got billions of people connected on social networks. And, that, of course, has exploded since then. Now, the reason why I introduce all of this, it seems to have very little to do with perhaps computer vision. is because I think it's starting to become clear to a lot of us in the field that when we look at the sort of overlapping sciences defined by robotics and the new area of contextual AI, so this is the interaction between wearable devices like Project Aria glasses and Ray-Ban Meta devices, and the advent of AI, internet scale AI in particular, then what we really start to see is a reflection of really the bigger challenges of understanding humanity. So think about it like this. The data that is used to drive the great LLM revolution only exists because social networks and the World Wide Web exists. If it didn't exist, the data wouldn't exist to train those giant LLMs on. That's kind of fascinating because certainly the order of operation was social networks were built because people wanted to interact and communicate. And so you have YouTube and Instagram and all the other sorts of blogs on the wider World Wide Web. But ultimately, that reflection of humanity is now captured inside of LLMs. And it doesn't look like it's going to change anytime soon. Certainly we'll see today the use of data sets that are more like simulation data sets and very technical data sets. But when we talk about scale of experience, it's the human experience that's being captured in today's AI. Now, we also have robotics, which again is kind of a reflection, especially when you think about like the potential for humanoid robotics that directly interface the world that we've created for humans. The idea is that if you're going to create a robot, it might as well be sort of humanoid because then it can interoperate with all the things that have already been built for humanity. So when you take these together, then what you can say is that in some ways, AI is a way of studying human minds and societies interacting. And, robotics certainly is a way of getting at the capabilities of humans interacting. But if we really think about the science of the problem, how is it that humans get stuff done? It's really a discipline in itself, of course, has overlap with the great social sciences and social psychology and all other walks of human science. But I don't think we really take it that seriously within our sort of more mathematical sciences. And the reason for that, I believe, is because we haven't had the tools to study it. And in that light, then I'd like us to think really for the first time about Project Aria being the very first time that we can start to study humanity at the individual level and hopefully over time at greater scales, not just to furnish our contextual AI capabilities and future products and robotics capabilities for our data sets, but actually to truly understand what is going on in our human societies. How is it, in fact, that we go from local interactions on a day-to-day basis to global societies with economies and ultimately civilization as we know it? And it's all done through humans interacting with each other now, and of course, growingly with humans interacting with AI. Okay. So let's have a look at these kind of bigger pictures. First of all, I want to ask a simple question that is a bit leading because it has an answer. Do our lives have a shape? So I want us to start to think about the larger scale patterns in human lives. And we're kind of fortunate because Kurt Vonnegut had a whole theory around this that he developed for his master's thesis. He sort of said, look, a life has a beginning and it has an end. And in fact, stories have a beginning and they have an end. And throughout a particular story, you can think about following the protagonist, and they might have good fortune and they might have ill fortune. They might have an unfortunate situation, or they might get very rich and have a great amount of joy. And he pointed out that actually, if you follow up across all different parts of our civilization, there are shapes of stories, and there aren't that many. He sort of like indexed, several of them, and I want to take you through some of them. But the point is that they all map onto the shape that goes from the beginning of the story to the end of the story, from a person's life beginning to the end of their life, or some segment in the end, taking shapes that kind of just transcend the actual content of the story itself. So here's a good one. This one is called Man in a Hole. And the story is, a man is doing just fine. His fortunes are, somewhere in the middle. And then he falls into a hole. And then he manages to get back out of a hole. And that's the end of the story. And the important thing for this story is that actually, after he gets out of the hole, he's slightly better off. Maybe he's better off because he learned something. Maybe he's better off because, frankly speaking, once you've fallen into a hole, things look a lot better than they did. But the shape is mappable onto a lot of stories that you may know from your own childhood and across our different societies. Here's another really famous one. This one's called Boy Meets Girl, although it's not specific to love. This one basically says, there's a boy, he's neither lost nor found the greatest thing. He has the experience of finding something he loves. He loses it, and then he gets it back again. And this particular story, again, maps onto things that you might see in your own reflections. The sort of more depressing side of stories are where someone starts in a very bad position, and it just, no matter where the story goes, it just goes downhill. It doesn't seem to get any better. And perhaps the most famous story of all, they say, is Cinderella, that maps onto a lot of extremely famous stories, including creation stories and a lot of sort of like societal creation. And it basically says somebody's in a pretty bad position in their life. They happen to get something from potentially a magical source. In the case of Cinderella, if you know it, it's a fairy that gifts various things to Cinderella over time, and her fortunes increase until one day she ends up at the ball, at which point the clock strikes and unfortunately she loses it all. But if you remember in the story, she gets it back again as Prince Charming comes along with the slipper. Now, the interesting thing is that this particular story maps onto some pretty profound, bigger histories of civilization. And like, why should it matter, these shapes of these stories? And it's like, well, when authors are penning these narratives, these stories are reflections on broader things in society. They're not arbitrary. And it's worthwhile imagining, if you can imagine any other shapes of stories other than these ones. There are a couple more. And of course, in reality, they wiggle all around as the sort of like time goes on. Okay, so that's a big picture. And the question is, to what extent is reality a sort of a story? And how can we talk about it that way? Now, what about at the more granular level? What's in the daily life of a person? Well, this is a view that we've been talking about now for about 3 or 4 years. We've basically been saying, look, if you're going to have these devices, these wearable devices that can get closer to the action, different from satellites in space that really couldn't penetrate, what was really going on. They would map Earth, but they wouldn't really be able to see what you're doing. Then you can start to get at the level of granularity of literally every single moment through your day. But when we ask, what is it that you need to represent? It's kind of like, it just keeps going. Is it important to represent the event of me brushing my teeth? Is it important to represent every time that I sort of like have a movement of my hand interacting with the dog bowl? Like, where does it end? Every eye movement might be important to the story of my life, right? It's interesting to think about that. That's a question of representation, which is very important, of course, to the reason why we're here, and look at the algorithms that are trying to represent our reality. So even the smallest moment, like a bit of exercise, might actually be profoundly impacted by something like my increase in heart rate that leads to a strange feeling, that leads to me doing something unusual. And if we don't capture the particular signals, the question is, have we lost the potential to represent a life? Is there no end to the granularity that we must represent reality? That's something to think about. At the other end of the spectrum, again, we've got day-in-a-life patterns that sort of like transcend the individual, but seem to produce macroscopic scale behavior. So this here is a day-in-a-life representation of Americans from the 2014 study that was then animated. I don't know if you can quite read the text down there. Let me see. It was based on the American Time Use Survey. So what's going on here is that 1,000 people are being represented at minute-level granularity as they transition throughout their day, minute by minute, and I've just sped up the simulation here. And what you're going to notice, of course, is something that I think, if you stop for a second and think about it, is that a lot of people are going through exactly the same patterns every day. There are some notable exceptions. Some of you may spot it if you've got a keen eye. But we started with, in fact, let me just start again now that you know what we're looking at. We start with the fact that most people are asleep at about 4:15 a.m. I got to tell you this morning, I wasn't asleep because of the jet lag from London, but that's an unusual situation. Most people are going to be asleep if they're in their own time zone. And as we set this simulation in motion, you'll see that it goes from sleeping to an interaction with personal care, from personal care to via traveling to work, from work to interacting with leisure. So people straight after work will travel often to leisure, and then they'll travel back home and do housework, some people, childcare, and other sorts of activities into the evening before finally again getting to sleep. So let's just watch this together as we see it happen. Eating and drinking, of course, everyone's got to do that at some point in the day. I'm not entirely sure what was in the miscellaneous category. These are the top categories, by the way, from the survey. So when you see up there volunteering, that's a significant part of the percentage of the people that were studied. Okay, we're getting into the evening now, a lot of leisure time, back into personal care as we then flow into sleep again. I see a lot of people in the pink work cluster at the bottom here going straight from work, straight to sleep. We might recognize that behavior in ourselves. Okay, so there's two levels of granularity, the fine grain and the very coarse grain. But none of this really talks about cause and effect. And yeah, if we're going to really understand the stories of our lives and how it is that the complex social interactions emerge from local effects, we kind of got to understand cause and effect. And so I could find no better example, actually, than one of my favorite episodes of Seinfeld. So hands up here who remembers the episode The Wink. Anybody? Just a few? Okay. Now, I haven't got the video, but I do hope you look this up on YouTube, because I can assure you it is funny if you look at the video. I'm going to keep it purely academic here for an analysis purpose. Now, what happens here is that Jerry is with his best friends in the diner that they often will be found in every single day. And he, for whatever reason of his diet that day, is eating a grapefruit next to Elaine. Elaine's like, "So it's a grapefruit today, Jerry." He's digging in. Anyone who's tried a grapefruit will know that the local interaction with that physical apparatus can be tricky if you're not an expert of cutting a grapefruit up, right? Imagine how we're going to capture that onto our personal timelines with Project Aria. Whoops, it seems as though some of the juice has squirted his best friend George in the eye. Now, one can only imagine the comedy that is going to ensue for an entire episode of Seinfeld on the basis of simply the setup of some grapefruit juice which is squeezed into his eye. Now, later that day, George Costanza is at work. He is working at the Yankee Stadium here, and unfortunately, he has an irritated eye. Who knows this story so far? Who can predict it? It's difficult, right? If you don't know it. Now, of course, his boss comes in and starts to ask George about some information about one of his colleagues who, from his point of view, is not quite doing a good job. And so George, who starts to, of course, try and interact with his manager in a very professional way, tries to give a straight answer, at which point his eye irritation makes him wink. And the wink causes his manager to say, "Oh, I see what you're saying, George. You're trying to be kind to your colleague, but actually he's obviously a bad guy." And I won't spoil the rest of the story, you should go and watch it. But this goes on several times because of this wink. This wink that is, in fact, not because he wants to wink, but because of just some grapefruit juice that's in his eye. Now, how are we going to tell the difference between the wink, because of some grapefruit juice that's in your eye, that actually does have an effect, for example, on your manager, taking some input in, and thinking that you're really saying something else, then, for example, when you really are trying to say something else to somebody. Now, think about where else this goes on. If you have children, you'll know that there's a difference between a look and the look. The look that says, "Stop doing what you're doing, otherwise I'm going to have to come over there and intervene with your behavior and get you back on track." Parents use it all the time, I'm sure. In fact, let me take a poll. Who's a parent here who knows how to use the look? Of course, every parent knows how to use the look. These are the kind of subtle behaviors that we need to be able to capture. Think about it. The children who you're interacting with when you use the look versus just a gaze in the general direction, they are already able to understand the difference between the two things. So I ask you this, are our AI systems on our embodied glasses ready for that level of understanding? Okay, that's cause and effect. Now, if we could start to capture this level of granularity, this is good cause and effect. When something happens out there, we all look over there. adding some levity to my presentation, the cause and effect graph. So this is something that I've been playing with now for a few years, and I still really don't know how to talk about it cogently, represent it graphically. I'm really struggling to imagine how, even if we had all that data for the scientific enterprise of understanding how humans do what they do, how we would really go about studying it, But let's look at it this way. If I was to say that there was Mingfei, Richard, Jakob, and Ashley all in a room, we could take some primitives, and we might imagine that we ourselves impact ourselves via thinking, whatever it is we're thinking. But we can also have these actions that cause other people possibly to have other actions. And so in that sense, then you can capture the impact of how an action causes another action. And in that sense, there is a cause and effect graph to be built at some point. So Ashley speaks to Jakob, who moves and speaks to me, who writes something to Mingfei, who speaks to Jakob, who then writes an email to absolutely everybody in the department. And so it goes that we could capture such a phenomena. Now, the question is, are there patterns in this cause and effect graph? And I want you to imagine in your mind's eye that you really blow this up to the scale of entire societies. Are there entire patterns that can be replicated and predicted? Are there things that actually represent something that when we look at the cause and effect graph, we say that is an argument happening over email between two people, with a couple more people on the email chain not interacting, but that's what it looks like. And I think the answer is yes. I think that this is the shape of human interaction that we can start to think about capturing at scale and start to detect or identify things that do map onto everyday language. But of course, to do that, we're going to have to be able to get those primitives. And I put it to you as well that those primitives that I put up there, which are just examples, like I said at the beginning, how fine-grained do those primitives need to be? Does the look need to be up there, etc.? Tone of voice, the raised heart rate that somebody may be able to detect, and so on. These are all the questions that we need to answer in this new science. Okay. At a completely different scale, we can start to look at this phenomena at a sort of more statistical level, at a level that is more akin to physics. And I did build a little simulator because I wanted to demonstrate a simple phenomena. Let's see how we're doing for time, James. Pretty good? 5 minutes. Yeah, we could do it. Should we try and do it? All right, let's try and do it. So I think I've got to, let's see here. I need to just extend, which is good. Network structures. So let's see. I built a couple of simulators. I'll just show one. It's time for one. Unfortunately, we weren't able to get my my screen to mirror, so I have to literally turn my laptop around so that I can see the screen over here. But I think that'll be all right. Okay, you can still all hear me, okay? Okay, so what we have here, in fact, I'm just going to turn a few things off to start with, is a very simple simulator. And I want to think of a blue dot here as being an individual going about their business in the world. You can see that I've got a couple of types of movement process. One's a random walk and one's a levy flight. If I just stick some sort of trails on, you can see what their movement looks like. This is like undirected random motion, right? Who here knows what a levy flight is? Anybody? No, okay. Well, I'll show you pictorially. A levy flight looks like this. So what you'll notice now is that there are big jumps followed by small little movements. A levy flight is a process that models, for example, animal foraging. So I might, for example, be looking for something, I can't find it here, I'll move all the way over there and have a look over there. It's also a pretty good model for things like eye saccades, so eye movements can be statistically modeled with levy flights, and so on. But I will keep it on a random walk because it keeps the conversation simpler. Okay, so there's a phenomena here where what I want to think about is a little bit abstract, but I think we can go there. I'm now going to show a radius around each one of these people, and I'm going to draw a black line if they are within that radius. Nice and simple, right? So of course this is just like a nearest neighbor based on a radius threshold. And as I increase this radius, when the graph turns red, it means that it is percolating. That is to say that there is a path from one node to any other node in the graph via effectively those n degrees of freedom that we talked about right at the beginning of this talk. Now, this has a particular sort of phenomena, which is to say that the graph becomes this way, has a large component that includes all of the nodes, and it happens within a threshold that is sort of very nonlinear. So there's a large region where this graph will not connect because there are multiple connected components, and then for a given radius, there's a point at which inevitably every single node will be connected via some degrees of separation. Okay, so that's all good. Now, the question is, what actually is a node representing? Is a node representing my location in space? Is it representing my belief about something in reality? Something, that perhaps is to be inferred? And is the distance, of course, not just space, but our distance in belief space? And the idea of when a graph is percolating in this way or forming a single large connected component, we can think about the fact that information can flow through such a network, and otherwise it can't. Now, this is interesting when we start to add in some behavior. So here I'll add some agency in, and I'll simply cause the nodes to start to flow in that direction. I'll turn the radius off. Now, the interesting thing about this phenomena is it sort of says, if we're all going in generally the same direction, in fact, we can have a much smaller overall radius with respect to our belief of a system. So let's have a look when we reset. You'll see that when I reset here, I randomize the nodes again, and it does not percolate. Well, it percolates, but very, very rarely. You see, it's not turning red. Now, when I turn on and let the agency go, you'll see that if we just give it a second, at some point then everybody's kind of going in the same direction. You can think of it as being squeezed into an agreement of thought space, and eventually then the network will start to percolate. There it is. So you can see there's two big components there. If we leave this going for long enough, what we'll end up with is the fact that as people have agency that align, in this case, in a sort of a conceptual thought space, then in fact the information can flow. And this is the value of having things like shared common goals. It's very interesting. Okay, so there's one phenomena I want you to keep in mind as we go through just the last bits of this presentation. Okay, so here's a simple question for everybody. If we are represented as one of those nodes, in space and time or in abstract thought space, how, without an external godlike figure, do we end up defining the actual systems by which any kind of agreement occur in the first place? So how for anything that says, this is where we're going to end up today, we know the way this works in practice today is because there are hierarchies of humans who are put in positions that say, organize each other. And we agree to that organization by those people, and so it goes, all the way from our socialization as children through the schooling systems into our adulthood. But if we're talking about here the science of the emergence of humanity, I ask you, how did that get started? How did we start to form clusters that in the end allow us to have systems of agreement? And so I'll leave us with just one question, which is, if we represent our networks of people and the edges representing something like, beliefs, and these circles represent the fact that I can continue to essentially propagate my own beliefs, and then I influence other people via these directed edges, what kind of algorithms allow for us to share information without it being top-down defined? And this class of algorithm, in general distributed computation algorithms, has an incredible place, I think, in this new science, because effectively processes like diffusion, or otherwise what are called gossip algorithms, become incredibly powerful. So I'll give you a very quick example. Imagine that everybody here was to come up with a number in their head and not tell anybody about it. And you can only talk to your neighbor, to your left. And if you're on the other side, you can talk somewhere else. So you can form a whole chain here, right? How could everybody end up with an average of all of the values in this room? What is the algorithm that will allow that to happen without a single person being given all the information and then summing it up and dividing by the number of nodes or the number of people? What if you don't even know the number of people? Are there algorithms that can do that? Does anyone know? So how do you get the emergence of a global average that everyone can agree on, given the value that every individual has? Does anyone know this class of algorithm? No? So this is a very interesting class, and it's sort of at the heart of how it is that local interactions can lead to global, convergent, agreed-upon phenomena. And I guess I'm making some big conceptual leaps here, so go with me. But the question is, it's not just a number that's in your mind, they're your conceptual beliefs. They're what you know and what other people know. And you have to be close enough in thought space to be able to communicate with that person. But at the end of the day, that is a form of diffusion that's going on across people. Now, I don't have time to show you this particular demo live, but I just pre-plotted it here. The answer to the algorithm, which is how do you come up with a global agreed upon average that everyone has while only doing local interaction, is you do nothing more than you take the value that you have in your mind and you pass it on to your neighbors, divided by the number of neighbors. And they do the same. And when you receive their numbers, you take the thing that's in your head, divide it by 2, add the average of their values, and you just keep doing that. And you can imagine if you're used to diffusion processes in more continuous spaces, how that actually diffuses information completely globally after a number of iterations. In fact, that particular graph I showed right at the start, just after around 6 or 7 iterations, will achieve actually very high precision on a global average, with no actual hierarchical definition of a leader, for example, that does the summing. It's very interesting. Okay, so this was a bit of a different talk for Aria, wasn't it? Yeah, that's good. We're interested in all 3 of these things, and I think the one that's just getting going is the one right at the top. It's the one where the biggest questions for those of us in the sciences will start to look now that we start to have the tools to do it. Now that we have Project Aria, especially Gen 2, we're in a position where the kinds of sensors that get at where you're looking, what you're interacting with, where you are in space, what you're saying, what other people are saying to you, they can start to furnish those primitives that for the cause and effect graph over time can start to represent our lives and our interactions, the web of interaction across time, which we can then start to do science on. And of course, it will be valuable for robotics and it will be valuable for contextual AI because effectively that is the great new source of information that will guide us into how it is that humans do all of the complex things that we do. So if we study humans, we will get great results, of course, for our synthetic counterparts. But I put it to you that it's an extremely exciting time to get actually back into what is going on with humans now that we have these new tools. Now today, you're going to see not just Simon showing, as he always does, that he only looks in a tiny region. So everyone probably has heard me say this at least 4 times now for the 4th tutorial. We now have the mechanisms with Aria to be able to know where you're looking and hence know, for example, what you may be reading. Some great work by Jin and team on reading in the wild. We have the kind of sensors that allow us to start to decode entire body poses so that what we're talking about here is not just a head pose in space, but an entire body configuration. So that, for example, it's not just the wink, it may be the point, it may be the wave, it may be all of these things that lead to the complex social dynamics when spun out over short to long ranges of time. And we have not just the individual self, but also the interaction of self with world, changing the state of the world on. I think it's one of the most profound things to think about, that all of the complexity that you see in the modern world in particular is a function of humans moving the world forward, often one brick at a time. Entire cities get built that way, entire countries over millennia have been built that way. All of the complexity of the room that you're in, not just the local configuration right now, but literally every structure was built by hand. Now, we're obviously entering an era where that may not be true. Automation by robots may change a lot of that. But luckily, all that robotic stuff, just like the internet, is all captured digitally. So we can understand it very clearly. Whereas the stuff that we do in this analog world needs this new set of tools to capture. I'm just going to leave you with this point as well. With the new generation of Project Aria, we're in a position to have very highly time-aligned as well as space-aligned devices. Now, some really good talks on SLAM, VIO, localization happening at this ICCV. I think Jakob did a talk yesterday. We're getting to a point where you really can rely on the space-time frame of the device. And that leads to the potential of thinking about how when multiple devices are in the same environment, they can be put together in the same frame of reference as a new distributed sensor. And that itself provides a new foundational source of data for looking at the world, not just through a single image, but through a full sort of like encapsulation of that space, separated by whoever the wearers are. Okay, beyond that, of course, we think about egocentric, because this is the egocentric tutorial, but it's hopefully clear to everybody that if a single person wears a single device, the potential of that device to garner information of the exocentric world is just as profound. So being able to capture the behavior and understand what's going on of others around us becomes possible, as well as the wearer themselves. Now, with that, I don't know if I'm getting a look from James. No, it's a wink. That's pretty good. Thank you, everybody. Have a great rest of the tutorial, and I hope to see you around the conference. Thank you.
I'm going to do a deep dive now into Project Aria. I'm going to give you some updates on Project Aria, and also some exciting news about Aria Gen 2 that I think a lot of people have been waiting for. So Ray-Ban Meta has been a great commercial success with now over 2 million devices sold since its debut in 2023. And we're now beyond what we would call a minimum viable product. And we're expanding functionality with devices that have displays, even more immersive prototypes that you've probably seen in some of Mark Zuckerberg's announcements in the past that are not shown here. So really we're expanding. And there are great experiences that are being developed on these devices that we're certain will essentially bring the next major wave in computing. They leverage LLMs and VLMs, which are amazingly able to summarize much of the internet when asked the perfect question, when summarized in the perfect way. But there's still the problem of doing that summarization and providing these models with the context that they need to be useful. And we're also at an inflection point in robotics, where we're now able to use human data to train robot policies. LLMs and VLMs are evolving into vision language action models, and robots can act directly from what they perceive. And glasses and robots perceive the world from their own perspective, and that's what we mean when we say the egocentric perspective. This is, after all, the egocentric tutorial. And it's really the embodied human perspective is one way we can think about the egocentric perspective. And in order to train these vision language models, vision language action models to operate in domains where they can offer value to us, they need to be trained with data that represents what we experience as humans. As you can see in this example, this is the hot 3D data set. I still think it's a very excellent example that just illustrates what egocentric data can be. We have the person's gaze indicating what they're focused on. We have what their hands are doing, hand-object interactions. This is all in 3D space. I think this is a very good summary of what egocentric data means. And as a community, we're asking critical questions about how much data like this is needed for breakthroughs in performance in training vision language models, how specific that data needs to be, how to formulate data sets that are effective for training and benchmarking. And I think we're coming a long way. Every time we have a tutorial like this, we see new advancements. So this leads to the mission of Project Aria, which really is to bring the human perspective to AI. AI is mostly about bringing internet information more effectively to humans right now, again, given this manually constructed context. But this is where we need to start thinking about a shift, about how we bring everything in our embodied human experience through multimodal sensing devices to AI systems so that they can better understand us and be massively more helpful to us. Over 290 research partners in 27 countries now use over 1,000 Aria Gen 1 devices. And these are the top computer vision, contextual AI, human-computer interaction, and robotics labs and companies worldwide. We now count 600 citations of Project Aria and Aria dataset papers, spanning a breadth of publications that focus on the evaluation of vision language models with egocentric data, to new innovations in robot training methods and foundation model development. And just earlier this year, we announced Aria Gen 2, our latest hardware with many improvements. We are working hard to make Aria Gen 2 available to the community in Q2 of 2026, and applications are open today for Aria Gen 2. I'll give a QR code at the end of this talk where you can go to a blog post that has all of the information that you need to submit an application for Aria Gen 2. I'll go into some exciting details about Gen 2 so you can start to formulate a picture of how this is going to work for you. So Aria Gen 2 provides a step change in usability and capability for the egocentric research community in several dimensions. It's more wearable with eight different sizes to accommodate various human factors. There are significant upgrades to the sensor suite. It has on-device real-time machine perception and audio to enable interactive experiences. So here's a view of the diverse sensor suite with an RGB camera, 4 computer vision cameras to capture a broad field of view, eye tracking cameras, IMUs, a magnetometer, a barometer, 7 spatialized mics, a contact microphone, a health sensor, PPG sensor for heart rate, a global navigation satellite system, and a time alignment radio. We are invested massively in sensor calibration, both at the individual sensor level, across sensors, and even across devices. And you'll see that this is a very difficult problem. We have calibration stations here for CV and RGB cameras, the microphone and speaker system, and our eye tracking cameras. And calibration is fundamental to sensor performance, especially for things like multimodal sensor fusion. Not only do we do what we call factory calibration before shipping these devices using systems like this, but we also offer what we call an online calibration for each recording that's sent to our SLAM processing algorithms that you can use. And I want to show you why this matters. So here we have a view of a high-speed camera showing a drop test of Aria Gen 1 glasses. And you can see extreme deformations of the glasses actually in this high-speed view. And these deformations can result in relative position changes of the sensors dramatically. This is an extreme view, but you can imagine even just wearing the device through thermals causes deformations like this. And here's a view of the glasses actually streaming sensor data to the NVIDIA FoundationStereo model for depth computation. And we're kind of purposefully bending the glasses as we're doing this. And you can see what a large result it has in deforming the depth result. So this is just a view of how downstream applications are affected by these deformations and why calibration is so important. Here we have the most sensitive application that we know of yet for these kinds of calibrations, which is a scene reconstruction. And we have a Gaussian splatting reconstruction. And this is the kind of thing that can only be achieved when you have online calibration, which we perform on each of these recordings. And if you look on the left, you can see the factory calibrated result is good. You can tell what it is, but it's not immersive. It's not fully realistic in the way that on the right, if you see the online calibrated result, you'll see the details in the trees, you'll see the spokes on the bicycles, and you'll see these cables being represented very realistically for 3D immersivity. And then the other thing that we spend a lot of energy on is, just as Richard pointed out with this idea of having multiple devices able to reconstruct a shared reality, you need to align sensors in time, so multiple Aria devices in time. And you can see on the left, without time alignment, the top and bottom two recordings, if you look on the left, the top and the bottom, if we really zoom in time and space, we can see a manual attempt to align these things is kind of pretty wonky. And when you get into trying to reconstruct at the multi-device level, it makes a big difference. With the time alignment that we've invested in, you can see very, very high level of detail on the right, almost perfect matching. And we can even measure this sort of thing. What we basically do is we have a special radio that facilitates transmission of the recording timestamps between the devices, and it's almost negligible. It's down to a 10 microsecond difference when we use these timestamps. And we can see that in some of these testing tools, these time measurement tools. Another thing I want to get into is just the quality of the sensors themselves. If you look at the computer vision cameras, which are a custom computer vision camera stack, the CV camera features 4.6 micropixels in a 512 by 512 array and employs an overlapping triple quantization scheme to enable single frame, single exposure, high dynamic range imaging. And the dynamic range exceeds 110 decibels. And what does that actually mean? If you look in the top left at the computer vision camera and you see the light turning on, you can actually still make out the filament, even in the midst of the bright exposure of the light. And you can also, at the same time with this high definition camera, see the background lighting. You can see the trees. So it's a really great achievement here. And the other thing, not just the high definition of the camera, but also the number of cameras we have and their spacing allows for us to achieve a very large field of view, both out to the side and down, as well as a large stereo overlap. And the large stereo overlap now lets us do amazing things when combined with something like NVIDIA FoundationStereo, which Michael and Bowen will be speaking about later. And by the way, we're also going to have an awesome live demo of this at our booth and a little bit later today, where you can actually use the system as an effective depth sensing head-mounted tool. So there's another way to look at the features of the device other than through the sensors. And we can look at it through a view of its interactive capabilities. So here we have a view of the basic ways that you can interact with the device. We have an action button for turning on recording, for example. The basic things like power and status. There's also a privacy switch. If you encounter a situation where maybe you did not have a consented person in a recording, you can flip the privacy switch and turn off the recording immediately. We have volume controls. You can connect the device to a Bluetooth audio source. You can imagine that audio source being something that's providing some kind of feedback to you. If you have the device connected up to a model. We have a contact mic. You can speak to the device. Let's say you have an LLM running in the background. You can actually set this up in a streaming way to speak to that LLM. And you can imagine all sorts of things. Maybe you're having it computing bounding boxes for you. You have some audio feedback. You can get extremely creative with the device.
You put the glasses.
I'm just going to show a video of a case study that we did with the company Envision, who focuses on solutions for the blind, to show you what I mean by audio interactivity.
You put the glasses on and you just talk to it like you talk to a friend.
Hey Meta, help me pick up some apples.
Certainly. Follow the sound to locate the apples in the store.
It'll start playing a beacon sound from the location within the store.
The glasses can actually map as they are being used.
We can allocate different points and label it with items that should be there in that space.
Apples are here.
You put the glasses on and
then another thing I want to show you, and actually I just want to pause for a second, talk about that demo a little bit. So actually Chungpung's going to give a demo of the client SDK and some of the ways we can build interactive experiences. And you'll see a little bit about what's under the hood when creating an experience like that. And you can think a little bit about what you would do when you watch him going through that demonstration. Now, the next thing I'm going to show is actually a view of our contact microphone, which is able to pick up audio by actually connecting physically and picking up vibrations, which can distinguish from ambient audio if you're in a noisy environment. So now you can imagine you're trying to speak to the device in a crowded space, and you can pick up your own audio much more clearly than the ambient audio.
Compared to Aria Gen 1, Aria Gen 2's unique.
You can hear the wind kind of overriding all the audio here, but with the contact microphone on, it's able to pick up the audio more clearly. Okay, so I'm going to switch frames yet again to talk about the device in the context of a very large advancement from Aria Gen 1, which is on-device machine perception. And Meta's developed a specialized custom coprocessor that also interoperates with a Qualcomm chip to achieve on-device machine perception. And for dataset creation, you can save enormous effort in long-duration recordings where MP signals get included directly in your recordings. And it also opens up the possibility of using the signals in real time. The Aria Gen 2 device has the ability to perform automatic speech recognition on the device. And this is an overview of the kind of data that you can get in real time from the device. We currently have hand tracking and VIO, visual inertial odometry, basically trajectory computation, running in real time on the device. And we're generally accelerating our process for how we, what you would call, lower an algorithm onto the device. And we're experimenting with all sorts of algorithm lowering. For example, like a hand-object interaction model, potentially lowered onto the device. And we're actually very open to ideas of what you might want to see lowered onto the device and potentially available for on-device computing. We're really open to conversations about that if you have ideas of what would be useful to run on-device. And when we provide Project Aria to qualified partners, we don't just provide glasses. We actually provide the Aria Research Kit. And the kit is more than just the glasses. It's a comprehensive set of tools for creating data sets and prototyping experiences. And at a high level, Aria Research Kit is composed of the Aria glasses, a mobile companion app, a client SDK, machine perception capabilities, and tools for working with Aria data. And we've observed that the community has two primary use cases for Aria Research Kit, and those are dataset creation. We now have a huge proliferation of externalized open source datasets from our community. Also, of course, from Meta, we also produce our own. And then also interactive prototyping. I showed the Envision demo, but you can imagine all sorts of things you might interactively prototype. And we foresee the community moving further and further into developing interactive prototypes once you have, let's say, a trained model and you want to run with it real time. So now I'll just dive into the companion app a little bit, which you can think about as a remote control for your device. And it offers a lot of functionality. You can pair your glasses, you can manage recordings. There's the concept of what's called a recording profile. This means if you have a certain set of sensors that you want to use in your data set creation or your streaming, and you want to run them at a certain frequency, let's say you want to run the RGB camera at 30 hertz, you want to run the CV cameras at 60 hertz, you want to use the microphone, you can turn on all these things at the right frequency to optimize power usage and to optimize for the size of the files that you create. You can set those in the companion app directly. And you can see a live preview of the sensors that you're using before you start recording, get confidence in what it is that you're going to be recording. And then another new thing that you can do in the companion app that Gen 1 users might be really excited about is you can rage shake. So you rage shake the device if you're having a problem, and then very quickly you can type exactly what your bug is, and you can communicate directly with user support in this very streamlined way instead of writing an email, for example. So you can just get it out there real time. And another way of interacting with the device, actually the most complete way of interacting with the device, is through the client SDK. And the client SDK is a comprehensive toolbox that will facilitate control and interaction with the Gen 2 device. You can manage the device, you can start recordings, you can stream with the device, you can record. We have Python and CLI tools for working with the device, and a whole bunch of example code for how to work with the device. And another great thing, again, is you can do this kind of interactive experience creation using the SDK, where you're streaming the sensors and machine perception signals to a PC or some back-end system. and then you're controlling the device and you're getting audio feedback or TTS feedback. So you're actually interacting with the device, as I showed in the Envision demo. So now I'm going to segue to talk a little bit more about machine perception. Aria Gen 2 can compute signals on device. I already showed you that in the device overview. But yet more can be computed in what we call machine perception services, which is an offline way for richer computation. And here you see some results from our machine perception services. We can compute hand tracking. We can compute also a closed loop trajectory. We can compute semi-dense point clouds. And I want to show a stunning example of semi-dense point cloud computation from the Nymeria dataset, which was just discussed, a dataset that ETH Zurich led. This is actually entering a tram, and you'll see the trajectory of this person entering a tram. You'll see all the semi-dense points, and they're color-coded from the observation. Basically, you'll see colored points at the time of observation when the glasses saw those points. And I think it's just stunning to see the length of the trajectory that's computed over the course of this tram going down a hill. And you're sort of seeing the zooming out. You can see the duration of the trajectory computation and the scale of it. And what's actually amazing is just the small amount of drift that occurs over this very large calculation. And you can see in the leftmost images, what you actually have is the computer vision cameras, and you can see the observed points happening, reprojected into the computer vision cameras. So really stunning example of our SLAM algorithms in action. And then you can see them actually getting off the tram side. This is one of the most impressive visualizations I've seen of our SLAM system yet. Okay, so not only can you compute a single trajectory, but over the course of months or longer, you could compute many trajectories in a shared space. And then you can compute a map of all of those, and then you can do a bundle adjusted SLAM calculation from all of these over time. And this, I think, is actually done over something like 20 or so recordings, computing one of our meta buildings. Okay, so I'm going to shift from SLAM onto a different topic and talk about hand joint pose computation. This is our 21 key point output computation. And this is something we made available a few months ago, and roboticists in particular have made great use of for articulate hand joints. And we now have an update coming out tomorrow in the MPS system to have more accurate hand joint computation in two ways. So the update that we will have will result in a reduction in loss of hand tracking. That means if you have a frame where previously you may have dropped hand tracking, you can see that in the top 3 images, there's a dropping of hand tracking. We'll have a great reduction in the loss of hand tracking. And then for the individual key points, and this is my best way to show you, if you look in the left, this is from the Hot3D data set, you can see the divergence from ground truth. So ground truth is kind of captured with mocap, and then we do our calculation of the hand joints. And you can see the divergence from the ground truth with the previous hand tracking algorithm. And so just keep an eye on how much the light blue diverges from the dark blue and the orange diverges from the red, as an example. So keep that in your memory. And now I'll switch to the new one. In the new one, you can see it's almost perfectly aligned. There's much less divergence happening. So this is a massive improvement in the quality and accuracy of our hand tracking, which again will come out tomorrow if you're already using Aria Gen 1. So Aria Studio is another tool that you can use to interoperate with Aria. Aria Studio is a desktop tool, and it's a great way for you to take recordings that are on your glasses and then download them onto your local machine and then submit jobs to the machine perception services to have offline computation. And you can see that workflow happening here. You can manage your recordings. You can request SLAM computation, for example. You can look at the result of a job. You can then even double-click and visualize the result of your recording. And so some folks may be already familiar with using this tool. And there's something I want to mention is that we have an update to Aria Studio that was just released in Aria Research Kit v1.15, which was announced, I think, yesterday morning or maybe the day before. So Aria Gen 1 users can now directly, if they have an issue with an MPS job, they can, after requesting the job and seeing some kind of issue, communicate with our user support directly from Aria Studio. So you can submit a case and say, hey, I'm having an issue processing this job. Can I get some help? And then we'll know exactly what job it is that you were having issue with, and we'll be able to work with you very rapidly over Aria Studio. It's a great advancement. And then we have Ego Blur for anonymization and data privacy. We're very privacy forward. And we've made this available for Aria Gen 1. And likewise, we're going to have this also for Aria Gen 2 once it becomes broadly available. Okay, I'm going to switch gears to talk about Project Aria Tools. Project Aria Tools is the way that you work with Aria data. So Aria recordings are made available in what's called a VRS file once you have them on your local machine. And this is a container that sort of houses multimodal data, and it has all of these different streams. You have your machine perception output stream, your audio stream, your computer vision camera stream, etc. So it's a very large sort of container for all your data, and these can be multiple gigabytes. And we've invested a lot in ensuring that you can have fast random access and iterators over this data, and powerful Python and C++-based visualizers of the data. So this makes it very convenient to work with VRS data. And actually, when we get to looking at recordings, Aria Kong is going to go through some examples of how to use Project Aria tools. So that was Aria Research Kit. I hope I gave you an overview of everything that you can use within Aria Research Kit. And I'm going to talk about some open source data sets and models that we have. And the biggest announcement that I have for you is that we have the Aria Gen 2 pilot data set. And this is a brand new data set. This data set is available for download immediately. You can go on our website and I'll give you a QR code where you can download this data set. I recommend that you do. This is one of the best ways to get familiar with Aria Gen 2 and the kind of data that it can output. We have all the sensors being recorded available to you. We also have all the machine perception output available, recorded from the device. We also have machine perception recorded from machine perception services. And it basically follows a subject through a hypothetical weekend of activities, doing things like walking, cooking, playing. We tried to capture a diverse range of activities so that you can see what the device is able to compute in all these different scenarios. And then a really cool thing that we also included here is the output from algorithms, including bounding box detection from our egocentric voxel lifting algorithm. We have also diarization, ASR, basically speech diarization, and heart rate estimation. And we also have depth from FoundationStereo included in this output. So it's a very rich data set. And another thing is it's computed from multiple Aria devices simultaneously that have been time-aligned. So it's a great data set for you to get familiar with what the device is capable of. And then other new things coming out now is Lingni is going to talk in a little bit about Nymeria++, which is an advancement to the Nymeria data set that was released at ICCV in 2024. And this year, Nymeria++ upgrades the data set in different aspects, including optimized human motion. And the latest models from Meta retargeted into SMPL for academic usage. And I'm just having some trouble with my video. It's not quite loading. Might be too large. I think I'm running out of RAM here, but Lingni will have a way better visualization of it as she goes through. And then Yawar will also present Shaper, which is a novel approach for conditional 3D object shape generation from casually captured in the wild sequences. And given a sequence, it leverages off-the-shelf SLAM pipelines to extract sparse point clouds and 3D detection algorithms to obtain for each object a set of SLAM points, pose multi-view images, and machine-generated captions. And a rectified flow transformer is then trained to effectively condition on these modalities and generate high-fidelity metric 3D shapes. So two drastically different releases, one around human body motion estimation and another around environment sort of estimation and reconstruction. And we also have all of our other data sets and open models. We have, I'm just showing several here that are generally categorized as object and environment reconstruction data sets and models. And then also models around people in their environments, so largely around the mission of what Richard described we're trying to achieve. And then some recent community highlights people will be talking today. We have ETH Zurich's Ego PPG, which really looks inside the wearer and understands things about what's going on both inside their psychology and their biological systems. We have the Nymeria data set, which is an outstanding benchmarking data set for city-scale SLAM. We have Georgia Tech's work on mobile robot manipulation, which is a new data set. And then we have Ego XOR from TU Munich, which is showing Aria in the operating room. It'd be really interesting for us. And I just have to show again, Anusha created this from the Nymeria team at ETH Zurich, a visualization from Nymeria going through the city of Zurich. I think it's just really impressive result, showing the trajectory visualized. I'll let that play. Yeah, I encourage everyone to download Nymeria and think about how to work with a benchmarking data set like this. These are all the Nymeria trajectories now shown live, covering a large swath of the Zurich city center. Okay, so what's next? The important stuff that you need to remember as you walk away today. Aria Gen 2 applications are open now. You can submit an Aria Gen 2 application now. That's both academic and corporate researchers. If you filled out what was an interest form, that was like a very lightweight form that we had basically since we opened up and announced Aria Gen 2, you still need to fill out an application. Applications contain way more detail than an interest form, and we need all of that detail to really triage the application. So please fill out a formal application. And Gen 1 applications are closed now. We're no longer taking Gen 1 applications. It's all Gen 2. If you submitted a Gen 1 application, we're still going to process that backlog. We'll get back to you. And we'll do that as soon as we can. And we'll still hand out Gen 1 devices for those that have filled out an application and qualify. And then if you're an existing Gen 1 user and you want to transition to Gen 2, you have to fill out an application still. And we're going to ensure a smooth transition for you. So we'll work with you on timing. We'll make sure we don't interrupt your ongoing research. And Aria Gen 2 is planned to be broadly available targeting Q2 2026. That's the current specificity I can give on timeline. And I'll continue to update people on timeline as we get clearer on exactly what those dates will look like. So this is your QR code that contains all of the information that you need. Yep, please take this as a recording. This is going to link to a blog post on the meta.com blog, which highlights for you links to the Aria Gen 2 device white paper. Goes into great detail on what all the sensors are, what they're capable of, what the device is all about. It gives you links to the application forms. It gives you links to the Aria Gen 2 pilot dataset where you can download the dataset. And it gives you links to the documentation where you can learn in detail about Aria Gen 2. So that is your main source of information. Okay, and so I've gone through, the highlight of Aria Gen 2. Now it's time to make this the hands-on tutorial that it is. And I'm going to pass things off now to Aria Kong, who is going to talk about recording and how to do a recording workflow. All right, Aria, come up to stage.
Hello, everyone. I'm Aria Kong. I'm the research engineer at Reality Lab Research. Today, I'm going to introduce you the next step in wearable AI technology, the world-leading multimodal AI device, Aria Glasses Gen 2, here. All right, so after you receive the glasses, you will have the research kit, which include the companion app. And right now, my glasses is already connected now. Let me wear the glasses. Cool. So as you can see the status of the glasses, like the Bluetooth, Wi-Fi, battery, etc. And in order to start a recording, you can click the custom recording button now. Cool. Then the first step is to fill the name of your recording. I put the ICCV demo here. Next step is to choose the recording profile. So profile is the configuration on what sensor to open for your recording. Let's take a look what is existing profile we provided. So profile 8 is a general purpose for recording profile. It includes all the sensors that we have, but we also have other profile to choose. You can also make your custom profile. All right, so from this page, you can see what is recorded here. Bluetooth, hand tracking, eye gaze, etc., which includes like basically all the sensors we have. Right now, let me start the recording. I'll click the begin new recording here. All right, so I'm already started the recording now. You can see there's LED light shining here. So Gen 2, take all you have with Gen 1, but just elevate all the sensors. Like James said, we have new sensors and much more powerful AI models running directly on device. Cool. So James just introduced the Aria pilot dataset that record a lot like different activities of human activities. I will pretend I'm like doing some like house cleaning, like folding the clothes. Okay, this is my clothes. I'm going to fold that. Look in my hands, and then because next visualization, we'll see how the hand tracking is working perfectly. And next, I'll move a little bit with my head because the visualization will show the trajectory, which is the position and rotation of my head. All right, so I've already finished the folding of my clothes. Let's complete the recording here. All right, now you can see it is successfully saved to my device. And the very good feature for the companion app is that you don't need to worry about the naming of your sequences. It will add to the name. You see the name is like up here with ICCV demo 2. So if you are recording a large data set, all the naming will be handled automatically. All right, so this command is to list all the recording on my glasses. So this is the client's DK, and this is the CLI for that. Oh, we can see that this is the recording I just take. You can see the recording UUID, which is the unique identifier for this recording. I'm going to copy that. And then next step is to download. Oh, sorry. Great. So this is using the command line to download the sequence. As James just introduced, we also released the Aria Studio, which is the GUI that you can have the interaction with the interface and try to see what are a list of recording that we have, which is like much like easier way. But with this CLI, you can do you have more flexibility. Cool. All right, we are going to download. Great, it's already saved to my laptop. I'm going to copy the name here. And the next step is to visualize this sequence. Great. As you can see here, so all the cameras, they are synchronized perfectly. The RGB camera, SLAM camera, and also the eye tracking camera. The pink dots here is the eye tracking. So I'm looking at the conference room. Yeah, I think it's this is when I was doing the introduction here. Great, and this is the 3D scene. You can see this is the glasses, and the blue line here is the eye gaze. And I want to introduce the trajectory here. We have two types of trajectory, which is VIO at 10 frequency and VIO high frequency at 800 Hertz. So this gives you a very precise pose and rotation for your devices. Oh, you can see I'm like folding the clothes right now, and the hand tracking and eye gaze works so perfectly. And on the right side, we visualize all the sensors we have. This is IMU. We have the left and right. And microphone, we have array of microphone, which give you focusability of the spatial audio. And this is content mic James just introduced, which gives you clear audio in the noisy environments. We also measure the pressure and temperature, and this is magnetor that can give you another signal. Yeah, so I've introduced you how to do the recording and make your next data set with Aria Gen 2. I'll hand over to Chen to give you more interactive experience with Aria Glasses Gen 2.
There we go. So Aria already introduced the recording capability. Now let's look at some real demos. This is running live on device, streaming live. On my try to break it. Let's see how that works. So remember, James previously mentioned there's a demo called Envision Spatial Navigation, right? It enables the device. You can talk to the device, activate the SLAM algorithm, which is my head motion that you can visualize here, and understand where you are. Also, this data can be streamed to some backend to process that. And if you have a location in that demo, for example, in Apple, it gives you spatial audio, which is also enabled through the stereo speaker on this device. It can give you a navigation guidance towards things that you're interested in. So this is the type of interactive experience that this device can enable. And this live demo shows that a lot of the components that can put this together. So let me demonstrate. Eye gaze, the green dot. I'm looking at my hands, tip of my finger. We can play what I'm looking at, but I guess you already know through this demo. We have hand tracking, 21 key point hand tracking per hand. Grab my phone and see if we can even detect my hand when it's behind the phone. Oh, catch that. I'm moving with object. Aria also showed that, oh, now we can't see it. There we go. Now it's back. On top of that, we have the SLAM trajectory. Those are all generated live from the device. And also we have the PPG sensor, which is the heart rate right here. Might be a little too much caffeine this morning. and you can also see the contact mic here versus the spatial, the audio from the external source. So if I don't talk, you can still, then when I start talking, you can see the contact mic start giving very clear signals. So this is the type of information that you can enable through the live streaming from this device, and also through a complete package previously introduced as the client SDK. So those are the data that you can stream from the device to the PC. To enable an interactive experience, you also want something that you can control from the PC to the device. Send a command, ask it to do certain things. Let me show another example. Let me turn this off. Press the button. This is off. I previously prepared a script. Let's see if you guys can hear it. So this is the feature called TTS, text to speech. You send a text to the device, it will talk to you. That enables the interactive experience.
Hello, my name is Aria Gen 2. Welcome to our tutorial session. It is a great day in Hawaii and hope you all will enjoy the conference here.
All right. So I'm Yawar Siddiqui, and I'm a research scientist with the Surreal team at Reality Labs Meta. And I'll be talking about our work Shaper, upcoming work Shaper, that's about robust conditional shape generation from casual captures that we worked on with my colleagues. So let's start by motivating the problem a bit. As James was showing before, with the Aria glasses on, when I walk around with my apartment, we can get different kinds of signals. You can see on the right that I can track where I am in the apartment, and with the machine perception services, I also get kind of like the sense of 3D space around me with these semi-dense point clouds. Given these slam points and the visual inputs, we can get a pretty good understanding of the scene around me. If you run some off-the-shelf 3D instance detection methods, such as the egocentric volume lifting or ImVoxelNet or 3D EDR. So the sparse slam points combined with 3D instance information now give a good understanding of the scene, right? However, for downstream tasks that need physical interaction, this information in terms of geometry might be too sparse. For that, you also already have solutions such as, again, egocentric volume lifting that can reconstruct 3D surfaces of the scene. Even from like the trajectory we saw before was kind of a casual capture. It's not a scanning trajectory. But with EVL, you can get some good estimate of the geometry. One issue with these geometries that you get with these kind of methods is that everything in the scene is the same mesh. It's a single monolithic mesh. So you see here the TV, the furniture is all fused into the same thing. And yeah, it's like everything is carved from a single stone, right? Because of this, these meshes cannot physically interact with anything else, right? So for example, if you throw a boulder on this, it won't interact as you would expect because it's all the same mesh. And also, objects here are incomplete, right? So if I were to segment out this sofa and then like just move around it, I won't see the rest of it, right? Because these methods don't have the generative priors to complete these meshes. Another issue with this monolithic scene reconstruction is the fact that usually you are tied with a fixed resolution budget for the entire scene. This means that for individual objects, you're going to share that budget. And this means that these might not get enough detail. So as you see here, the lamp, the chair, and the table, they don't quite get details. Like the chairs don't have slits in them, or the table is kind of really blobby. So to this end, we introduce Shaper. And let me pause here. So this is a new method, and it does object-centric 3D reconstruction. And for each of the detected objects that you saw from EVL, it would extract out post-image crops of the object that we're reconstructing. We'll have the slam points for that object. We'll also have a machine-generated caption, the couch with pillows here, and some mask prompts. And for this, from these inputs, what this method can do is, let's play this, complete the, generate a 3D reconstruction for the entire shape. And this you can do for each of the objects in the scene. You do it for each of them, get the same input for each of them, and run it. And what you get out is an object-centric reconstruction of your entire scene. Now, this approach to 3D scene reconstruction solves some of the issues we mentioned before, right? Like, so since each of these objects are individually reconstructed, they will move individually. They also get enough detail for each of these shapes, so you get a more faithful reconstruction of the shapes, right? So like you see that the table has enough detail, the couch has enough detail, the chairs have the slits in them, and now, so since you're doing it object per object, you get this detail out. And also, as I mentioned, like it's now a compositional object-centric reconstruction rather than monolithic, so physical interactions can be now simulated more plausibly. Now, Shaper builds upon the progress of image to 3D generative models, so we should talk a little bit about them. In the last 2 years, image to 3D has become exceedingly good. We've gone from class-specific models. There was days where we could only reconstruct chairs and tables. Like we would train one model that would reconstruct chairs, you would train one model that would reconstruct tables. Now you have models that can go from any picture of any object to a 3D, like a really faithful 3D reconstruction. I would even say that at this point, conditional 3D generation to this limited case is close to solved. And people have started moving to harder tasks, right? Like, so in the lower right, you see Bang, which moves on to the task of part-based reconstruction now, not just the object. You have methods that move on to articulated object reconstruction. However, I would say that this statement, while true, there's a qualifier here. These methods can only work good for very clean, very clear, unoccluded, segmentable inputs. When you have something real, like what's shown here, right? In the real world, when you move around, you'll see a lot of occlusion, objects behind other objects, and like a lot of these methods segment out the object in consideration before they run the algorithm. If you run segmentation on these kind of inputs, even manually doing it, you might not get the whole shape because it's occluded. If you run something like SAM, even if you click a lot, you won't get like very good segmentations. And then again, like some objects are just maybe not noticed by too closely or may have too much sensor noise. And in effect, what you have is the reconstruction with these algorithms are not so ideal as we saw before. Here are some more examples of the scene that we saw before. And you see that like if the object is occluded a little bit, it will get cropped, or you have some artifacts as seen in this chair here. So in Shaper, we were exploring how to make object generation robust when input comes from more casual in the wild setting. So let's go step by step of what Shaper is, right? Like, so from the very basics, Shaper is simply a diffusion or flow matching model that uses a transformer denoiser that works in some latent space. So much like any denoising transformer, it runs not on the raw shape, but on some latent space. The latent space we use is a vec-set representation, and this is very common in like state-of-the-art 3D generation approaches. Next, we want to have some sort of control of what we're reconstructing, and this is why we condition on multi-view images of the objects that we observe. So we extract out Dino V2 features and embed them with plucker arrays to give a sense of where these images are coming from. And these stream of tokens then go to the transformer where they can be attended to. However, if you just do that, that's not enough. What we see is like, it works sometimes, but sometimes you see these kind of inputs which are less than ideal. Here's another example. Now, one thing that really helped, we found that if you condition additionally on the slam points, this increases the robustness a lot. So here I extract out some features with a sparse 3D ResNet and pass those tokens on as well to the transformer apart from the image tokens. And yeah, this gives significant improvements. So for the shapes that I showed before, on the left you see without points, on the right you see with points. And this improves the quality of the shapes a lot. However, we noticed that in cases where, one more thing I need to mention here is once you do this kind of SLAM conditioning, like other approaches, what they would do is like they would segment out these images before they reconstruct. With slam points, you don't need to do that. So you can, the network can figure out from the points and their correlation with the images, which object you're trying to reconstruct. So you pass on the images with the background here. However, we noticed that there are cases where the network would sometimes reconstruct part of the objects which are very close to mesh. So here, I don't know if you can clearly see, but the bench is very close to the table. And when you're trying to reconstruct the bench here, the part of the table gets reconstructed. And here's another example where the cutting board is very close to the kitchen roll, and that also kind of gets reconstructed here. So to make it a little bit more robust, we find that if we take the points from the images, project them to 2D, and use them to prompt the dyno features, this kind of resolves the issue here. So the intuition here is that dyno features have enough information, right, to segment out the object. They already know like what different objects are represented by different dyno features. However, you still need to tell the model which is the object we're trying to reconstruct. And that's what the points do. They kind of prompt the dyno features like, this is the thing I want to be reconstructing. And this solves this issue of extra objects being reconstructed here on the right. Lastly, one more modality we leverage is machine-generated captions that can guide the denoising process. So the idea here is like all the other modalities we talked about, the images, the slam points, they can be incomplete, right? Like images can be hidden by other, like the object can be hidden by other objects in an image. Slam points might be incomplete, but text is always complete by definition, right? Like if it's a table, it's a table. There's nothing more to be described in terms of completeness. So that kind of guides the process a little bit more. However, doing all this multimodality, the model is not robust enough, and we still see cases where you get less than ideal reconstructions. So what we do is we make a lot of augmentations on all the modalities. So on the image side, we have a lot of object background augmentation, some foreground background augmentations, sensor noise augmentations. On the point cloud side, we have a lot of augmentations in terms of simulating partial observations, different kind of dropouts to simulate half point clouds, adding some structured noise. And one important thing we found here is that when you want to do these augmentations, you want to do it in the data loader. So you want to be able to do this on the fly and not like just process them and store them in the on your disk, right? Because what you want is like kind of an infinite data generation, basically. And when you do all these augmentations, this helps a lot. So you see there, like if you turn off any of these augmentations, you don't quite get the effect when you have both of them. However, this is still not enough. And the thing is, if you train with only large-scale object-centric data on the left, shown here on the left, these are great. These data sets are like diverse. There are millions of objects. You kind of learn objectness with this. But even after all these augmentations, they are very synthetic, right? Like that's very made up, right? Like all the augmentations that you're going to do are going to only replicate how real life would be. So to make a change to that, we do a second stage of training with much more realistic inputs from Aria synthetic environments dataset. So we go over the whole dataset, we extract out crops for objects, and these are much more realistic. You get much more realistic occlusions, you have better point clouds on how you'd see in real life, and this also helps a lot. So with this in place, now you have a method that can like reconstruct real life things like chairs under tables and tables with chairs around them. Yeah. And this kind of is what the method is. It's a rectified flow matching transformer working with a vec-set latent space, conditioned on multi-view images, slam points, 2D point tracks, and machine-generated captions. You train this with a lot of augmentation, which is on the fly for each of the modalities, and you have a two-stage curriculum training that makes for effective generalization. Now, how do you evaluate such a data set, right? Such a method. So there are many object data sets in the wild. There's DTC, which captures, which has a little bit of a control setup, right? Like you have an object placed on a table and the user goes around it. So it's not quite the casual setup we're looking for. The good thing about DTC though is like it gives complete objects. So we can evaluate against a good ground truth. On the other hand, ScanNet is very casual. You have captures of objects on how they would occur in real life, right? Like you have chairs and tables, it's a mess, right? Like it's how real life is. However, the ground truth geometry in these cases is very bad, right? Like it comes from a scanner, it's going to be incomplete. You don't want to benchmark your method that produces a full shape against this. So to this end, we also introduce a Shaper object evaluation dataset that has 178 object sequences across 7 scenes, and each of them are individually complete objects. And yeah, they cover a wide range of categories like tables, chairs, also small objects like lamps or devices, artworks, and so on. So we compare our method against multi-view to 3D. We find that compared to the EVL model or even FoundationStereo running on Nebula on Aria Gen 2, it's much robust compared to methods such as LRM, LIRM, DP Recon. Our method is much more robust. Compared to image to 3D approaches that we build upon, even when you give like a really manually selected, really nice view with segmented manually with SAM, we perform much more better since we are much more robust to real world cases. Finally, compared to image to scene methods, which can take single or multiple images, we find that these approaches struggle in terms of placement of objects and their relative sizes, like shown in the middle 2 rows, while we can do a much better job with this. Just like any other method, like this, of course, has the limitations. When the sensor resolution is too low, the objects are too small, we struggle with the details. And sometimes you see in the model, you tend to reconstruct more than what the object is. So here in the input observation, ideally what you'd want is reconstruction of the table for the box that detects table and rest reconstructed individually, but sometimes we reconstruct more than that is. And one more fundamental limitation here is that since we're dependent on instances from another method, if those are missing, we're not going to reconstruct those. So just as a quick recap, this is Shaper, and it's an upcoming method. It's coming soon on the website. And in the talk, we highlighted the need for object-centric reconstruction and the problems with generation in the wild. And we introduced a method for conditional object generation using multimodal conditioning with heavy streaming augmentations and curriculum learning. And we also introduced a dataset for in-the-wild object reconstruction evaluation. Thank you.
Hi everyone, my name is Lingni Ma. I'm a research scientist from the Zuria team. So today I'd like to talk to you about Nymeria++. This is an upgrade to the previous released Nymeria dataset. And we want to upgrade the dataset to empower human motion understanding research in an even better way. So for people who are not familiar with what Nymeria dataset is, this is basically a massive collection of human motion in the wild. The team released the dataset last year at ICCV 2024. So the dataset was recorded with multiple Project Aria Gen 1 device and Gen 1 alike wristband and motion capture suit. All of them are time-aligned and spatially localized in one metric 3D world. And the dataset is annotated with the ground truth, body motion, the human written narrations. As of today, the dataset is still the world's largest human motion in the wild and the largest collection of human motion with natural descriptions. So to help you visualize the quality and diversity, this video actually shows you random sampled 100 snippets from the Nymeria dataset. All right. And on this slide, I briefly summarize the key statistics about the dataset. As I mentioned, the dataset is actually fully released last year. So with the QR code, it will bring you to our website where you can already download the data, the code, the paper, or just simply visualize the data online and filter the sequences and modalities as needed by your research. So before diving into the details of how we upgrade Nymeria dataset, let me first briefly mention a few research study cases that are uniquely empowered by the dataset. So the first one is the algorithm that we developed to track egocentric full body motion from a single pair of smart glasses, such as Aria Gen 1. So this is a very challenging problem because with the form factor of the smart glasses, even with multiple cameras, they hardly observe or provide any self-observations. And traditionally, in order to solve this problem, people typically need to wear multiple motion sensors in order to estimate their own body motion. Now, this was changed when we start to use Nymeria, where we show that given a large quantity of training data, we can actually learn a machine learning algorithms to infer the egocentric body motion. We named this algorithm HMD2. So at its core, this is a diffusion algorithm that generates the full body motion conditioned on the headset trajectories, the hand tracking, image embeddings, as well as the surrounding point cloud. Now, in this video, we show the result of HMD2 in tracking the full body motion from a single pair of Aria device. Again, I want to remind you how little information the egocentric videos actually captures the self-body motion, yet trained with a large quantity of data and leverage the environment context. The network is actually able to make very reasonable predictions. So the nice thing about the algorithm is that it actually explains the ambiguous motion state by a probability distribution, since we use diffusion to frame the problem. And to visualize this distribution, we actually sample the model 10 times and overlay the output. So if you focus on the hand, you will notice that whenever the hand appear in the view, the distribution is actually collapsed to a very tight distribution. However, when the hand move outside the field of view and hand tracking become unavailable, the model is also able to give you very diverse and equally plausible poses. Now, the second case I want to share is another powerful modeling technique that we'll also explore to build generic foundations for egocentric motion understanding. The algorithm is what we call EagleOM. So this is an algorithm designed around 3 principles. First, we want to model the human motion as language in order to harvest the power of large language models. So this is logical because both language and human motions are sequential data with very strong continuities, where transformer and next token autoregressive prediction is very suited to model the transitional probability, the short-term and long-term context dependencies. So we want to use, the second one is we want to use a generative modeling technique. So we can sample the distribution to still represent that ambiguous motion state. The third principle is we want to model actually the joint distribution of all the modalities together. For example, the body motion, the language descriptions, as well as the multimodal sensor measurement. By doing this, we open the door to unifying the framework to achieve multiple motion tasks by later marginalize the joint distribution. For example, we can now condition motion from video or text or vice versa. So this basically brings EagleOM into a very similar training paradigm as large language models, which means we will tokenize the human motion with VQVAEs, and then we expand the vocabulary of large language models by pre-training, and the last we fine-tune the model to achieve multiple tasks. Now, I actually want to show you some interesting tasks that EagleOM is able to perform, starting from a relatively simple one, where we use the headset and erase the 6-off trajectories to predict the full body motion. So this is typically known as the 3-point body tracking problems in graphics. We compare our solution with 2 state-of-the-art solutions as Avatar Poser and Body Fusion. So earlier I said this problem is actually relatively easy because if you know the 3-point trajectories from your head and hands, your body motion, especially the upper body motion, is pretty well constrained. However, as shown in this video, EagleOM often gives much more stable and accurate predictions of the lower body, while the other baselines from time to time struggles. This is also observed in the second examples, where our algorithm predicts more plausible solutions with respect to the environment, whereas the baseline algorithms often penetrate and produce implausible motion. And let's remember that this is a very challenging cases where the lower body is actually not observed by the input. Next, I want to show you a bit more challenging cases where we remove the raised conditions and only use a single point to infer the full body motion. And we compare this our algorithm with Eagle, which is a diffusion-based solution. Now, what we observe here is Eagle OM is able to give much more accurate poses in general. And in this example, we also observe that often Eagle OM is able to give more accurate and more energetic hand motions. Last, I want to show the most challenging task that Eagle OM is able to perform, which is to jointly predicting the parametric body motion as well as the language description. So for this task, we actually didn't find any existing solutions. So we shown the output of our models and compare the ground truth motion to our predictions. So in this demo, what you see here is the description on the right is often very detailed with in-context informations. For example, it is not just describing how the person is moving the body, but often describing the environment where the person is looking at and how the hand is interacting with the environment as well as where the person is. Now, this is just another example to show you a diverse scenarios of what Eagle OM is able to handle. Okay, moving on with the third study case, which is for the axle body tracking. You might think people have been studying this problem for decades and it must be a solved case. But actually, if you take a closer look at existing solutions, you will notice that most of the algorithm largely focused on single view videos, which leads to the scale ambiguities. Furthermore, cameras are often static or only move slightly or slowly. This is actually not the case when you wear smart glasses on your head. In this setting, we emphasize that any solutions to estimate the axle body motion should be spatially aligned with the same metric 3D world with the rest of the spatial context output. So in order to address these challenges, again, we train an algorithm based on the Nymeria dataset. And here I want to show you the exciting early results that we already achieved in our early experiment. So actually what we're showing you here is the algorithm trained on Nymeria dataset, but inferred on Aria Gen 2 device. So what it's showing here is our colleague Nan grabbing lunch with his friends at the cafeterias. As he moves around, we track almost every single person observed in the egocentric cameras. Note that how many people are populated in the same metric space and are all spatially aligned with the world coordinates. And I also want to point it out that thanks to the collectively 270-degree field of view of Aria Gen 2 device, people behind the egocentric wearers is also well tracked. It's almost like you have invisible eyes. Now, the detail of this work will come out soon, so stay tuned. Now, in addition to the work that is mostly developed by our team, we also noticed that the dataset has been gaining attention in academia research. Listed here just a few recent publications where we see research projects uniquely enabled by our dataset. For example, people are using the IMUs to infer the body motion as well as to output the text descriptions. They also are using the body motions to condition video generation models or even jointly predicting both egocentric motions as well as the videos. All right. So let me switch gear and start talk about how we actually make the dataset even better into Nymeria++. So this brings me to this teaser video that gives you a glimpse of what Nymeria++ actually is. So I'll just let the video play for a moment. Obviously, there is a lot of things going on. There's body motions, and there's seeming like bounding boxes. So let me actually break down Nymeria++ into 3 major axes that describes the upgrade. The very first upgrade is actually along optimizing the body motion as well as the body shape. So in the previous Nymeria dataset release, we actually mostly solely relied on the Axon's motion capture suite to give us the ground truth motion. The only modification we did is to align the body motion into the metric 3D world as the rest of the Aria device. The motion artifacts, however, are often not addressed, such as there's foot sliding and inaccurate end effector motions, especially observed with the hand. And in the previous release, we also use a relatively simple algorithm to retarget the axons motion into a Meta's human model without much care. This is mostly for visualization purposes, and this also leads to some non-ideal shapes. Let's see if I can play this video. Oh my god, it's really hard. Okay, it doesn't seem to like to play. Anyways, okay. Anyways, if the video doesn't play, but with the view, you can already start to notice on the left, you see the original vision, body retargeted into the human model. On the right, you see the latest results from Nymeria++. So in order to get these results, we actually improve the upper body motion using the wristband tracking, which is way more accurate than IMU-based tracking from the motion capture suit. We also reduce the foot sliding using the velocity of the feet as well as the foot contact with the floor. The third thing is we also retarget the axon's kinematic motion into Meta's latest and greatest human motion model, which will be released by the end of this month. And the last thing is we paid particular attention to how we retarget and optimize these shapes and motions, and particularly also retarget them into the simple format, where we heard a lot of feedbacks of how people would like to use these different human models in their research that can potentially unify Nymeria with the other motion dataset out there in the wild. All right. In addition to motion, the second axis we upgrade is actually to enrich the dataset with dense 3D bounding boxes annotations for almost all 900 indoor collections. The reason to add this annotation is motivated by the principle that the human motion is actually a function of the environment, so the environment should be a very useful context to infer body motion and understanding body motion. And with these annotations that we did, we're not only including most common objects categories, such as the chairs, tables, plants, storage, cabinet. We also include structures of the space, such as the walls, floors, windows, etc. So in this video, we actually shows the fly-through of 47 unique Airbnb locations, which are all densely populated with these bounding boxes and structures. And to help you further visualize the quality, we projected these 3D bounding boxes into the Aria RGB view to show you how accurate and dense annotation is. I also want to briefly mention some of the statistics of these bounding box annotations. So they are mostly derived from 47 base map annotations, where we have all the recordings spatially localized into the same coordinates. However, we do not do a simple transfer of these base map annotations into individual recordings. We also fine touch on each individual recordings to remove objects that has been moved and refine the annotations. So this brings us to 19 predefined object classes, where we have a little bit close to 12,000 semantic unique objects. We also add a free-form categories that can describe anything that you can observe at the home. So this brings us to another close to 10,000 unique instances of objects that you can observe at your home. Now, the third upgrade we did is actually focus on extra data and modalities that are previously excluded from the release due to various reasons. And these additional modalities include additional hours of data, new base maps recordings that we use to annotate all the 3D bounding boxes. We also are including 600 hours of wristband videos, where they can be particularly interesting for robotic learning because they provide video perspectives coming from your wrist, coming from your hand. The fourth thing is we're also including 600 hours of audio data recorded also with the Aria device, particularly useful between the participants and the moderators. There has been a lot of interesting conversations going on. Last, we're also considering adding object-dense reconstructions using the shape-R algorithms you just heard from my colleague Yawar. Okay, to conclude my talk, I'd like to show you this video. This is actually not a Nymeria dataset, but it's an algorithm that's a lot of algorithms that is built on top of Nymeria dataset, and this is inferred on the Aria Gen 2 device. It actually shows you a very good concept of what we want to build and achieve with the Nymeria dataset. And with that, I hope this can inspire people to better use, make better use of our data. So Nymeria dataset will be released by the end of this year. Please stay tuned, and you can get the update from the projectaria.com. With that, I'd like to thank all the amazing people behind this work. Thank you.
Hello, everyone. So yes, as said, I'm going to show you our trip towards common sense and robotic perception. So as you might have noticed, the world was not made with robots in mind. Sorry. Okay, so as you might have noticed, well, it's not meant with robots in mind, especially in the latest years. We had this movement of like minimalistic environments. We want everything without knobs, without making any noise, without textures, without colors. And of course, this is a huge problem, especially for roboticists. So if any of you have worked with hardware, it's a pain. So of course, this causes a lot of questions, especially for robotics. First of all, spatial representation. As you might know, here it's a computer vision conference, so of course, everyone's doing point clouds, everyone has huge 3D representations. But if you have hardware, you cannot do that. It doesn't work. We have limited compute. Then, so how do I represent the world? Then what happens with dynamics? Okay, I have a static representation now, but what happens with things that move? Then further, the human in the loop. We want to do this actually, to have robots interact with actually humans. So what happens with that? And then there are much more questions there, of course. So I will tell you our storyline on how we basically have been kind of like addressing these things. So let's start with the first approach to robotic scene understanding, which is Spot Compose. So Spot Compose was a very motivated master student that decided to try out pairing computer vision with robotics. So we have at the beginning a scene reconstruction, which we have 3D instance segmentation on top, which you can see, and then we had two approaches. The first one, we have object retrieval, and the second one, we have drawer manipulation. So in the first part, we have basically the different grasps. We establish with the deep learning network the ideal grasp, and then in the second one, we actually detect where is the handle, where can we interact with, and then do an interaction. So this looks like this, actually. So you can see Oliver is asking the robot for a water bottle. And basically, you have the 3D segmentation. We, of course, need to find first where the bottle is. There you have it. We try to find the ideal grasp. And there. Now Spot is performing the act. This looks all extremely slow because basically the robot tends to break things, and he tends to break himself. So that's why we put everything actually very slow. And you can see there, in the end, he manages to bring the water bottle. And then, basically the question that we all had, where is my keys? Well, here in this case, Spot is searching in his drawers, where are the keys? And he is basically doing what we all would do. We look in the drawer, where is it? Well, there it's not. So in this case, the search is quite short. He basically, as you can see in a second, he manages to find it actually in the second drawer. So actually now we have a robot that can bring us objects and it can search for us things. But this basically brought us to some conclusions, which is, well, point clouds are way too heavy to represent the world, especially on a robot. And second, what happens with dynamic elements? But at the other side, robotics and computer vision are great tools to pair with each other. So we did the next step, which was Spotlight, which was presented at Humanoids 2 weeks ago. And so Spotlight has still the same starting point, but in this case, what we did is we have the moment 0. So we basically create from that 3D scan and the instant segmentation, we create a scene graph. That scene graph is basically our static initial assumption. And then from there, we basically, like in this case, we're trying to find light switches. So we basically find the light switch semantically. Then we do post-refinement, since the graph in the end has 3D information, but because in the end, the nodes are the instances and the edges are the distances we get from the map. But of course, we don't have an accurate position. So we do post-refinement, and then we do the affordances. In this case, the affordances mean what type of light switches is it? So double light switch, do I push in the middle? Do I push up, down? That's what we mean here in this case. And then we can populate our scene graph, which in the beginning was metric with actually functionalities. So first of all, we bought every light switch we could get in Switzerland, and we had Spot try them out. I think it just looks very nice to see him doing all of them. And this is basically how it looks. So you can see here, we have the 3D, then we have the scene graph. It's not visually appealing to look at, that's why you will see it in a 3D point cloud. But basically here, Spot is doing the post-refinement. He basically finds the light switch, clicks the button, and now he's doing what we all would do, which is, I know where the lamps are, let's check which one actually changed state. So it's basically checking, there are 2 lamps, which one turns, and now we can actually connect 2 nodes with each other, basically with the functionality, this switch turns on this lamp, which is what you would do in your memory when you enter an environment that you don't know. So here's now trying the second one. So basically what we can do now is we can pair a scene graph with 3D information and add functionalities, which is actually like creating a memory that also a human would have. So this brought us to some conclusions, which are basically most interactions can be reduced to linear and rotational motions, and the power of scene graphs. So they are nicely interferable with VLMs, and it goes beyond physical connections. So this is actually like a huge power for us. So now we added the human in the loop. So the setup is the same as in Spotlight, but we added now a human with Aria glasses that is basically like recording and interacting with things and dynamically moving things actually around. So what you can see is like basically we first do hand object tracking, and then we do the point tracking of the object that is actually moved, and then we update the scene. So here you have Tjark. He's interacting with this nice picture frame, and he's basically moving it. But now you can see actually the node of the frame is moving while he is actually interacting with it. And we can dynamically update the scene graph by reconnecting the node to the closer ones. And so we can actually track dynamic elements now in the scene. Of course, we need to be able to see them. But you can see here that basically we have some kind of byproduct which we can learn, which is the fact, so Tjark is here hiding the plushie in the drawer. And basically, Spot can imitate the same trajectory. So he can actually, without having to do reinforcement learning or imitation learning, just imitate the same kind of action that we have from the Aria glasses, which we get out of it. And basically, also something that I really liked is the fact when we hide things in drawers, it's not that they are gone, we just cannot see them. Well, the scene graph allows us to actually connect this, have the information that the cow in this case is hidden in the drawer, and this information can be accessed by the agent that is also in the scene. And then we can actually like basically go ahead, find the cow, and in this case, reunite the cow with the plush monkey that is sitting on the yellow chair. I'm going to give you a second to enjoy that part. There you go. So the conclusions, of course, here, scene graphs are for us the way to go. They are lightweight, effective data structures to understand the environment. We can easily update them with dynamics, and it offers endless opportunities to add information. We can literally store everything we want in it because it's a dictionary in the end. So can we do multi-agent? Well, yes. We added a second spot. In this case, this one had a basket. The one with the basket is called Softy. The other one is called Fluffy. And basically, you can see they are assisting each other. On one side, the one is basically checking the light while the other one is pushing it. And on the other side, basically one is getting the object out of the drawer while the other one brings it to us in the basket. So you can see that actually like underlaying all of this is a scene graph, which is shared between the human that is deciding what tasks to do and the robot that split basically the information, who can do what. One can carry an object, the other one can pick it up. So of course they are sharing and splitting the tasks. So overall, we have now a light rate representation of the scene. We detect and track dynamic changes, we identify functional properties, and we create a shared memory between humans and operators. But three things are missing. Can we align cross-device experiences? Can we upscale this from a lab setting to a real environment? And is there a knowledge transfer between humans or robots? So this brings us to, we all have different viewpoints, which is Crocodile. Crocodile is the data set that we created 2 years ago, which is like 10 locations, 7 new ones plus 3 from the Lamar data set. It has temporal changes and 10 centimeters ground to accuracy. And this uplifts the entire thing to actually real world environment. So just to give you an overview, these are the most used visual localization data sets. And if you just take the ones that have multiple agents, we're left with this. And then if you just take the ones that have many locations, we're left with this. And then the two that we're left, one is synthetic. So we have the gap between synthetic and real. And the other one literally has an overlap of 2 agents per scene. But indeed, this is kind of like, it's also all on a brick on top of the agents. So you're not using the original kind of cameras. And then we have Lamar, which was the predecessor of Crocodile, which basically had mixed reality and handheld devices. But Crocodile adds drones and ground agents to this. There's the sequences. It's also much more than the others. So if you ever wanted to have your visual localization and SLAM pipelines running on Swiss bunkers, now it's your opportunity. So you have actually like multiple catastrophe scenarios, which we recorded. And here you can actually get a fly through to them. One is the Sukkulentensammlung, which is a plant collection in Switzerland. And the other one is basically like a hydrology lab where they simulate water dams in small scale. So you can see the blue one is Spot. Then above, we have the handheld device. And then further above in green, it's actually the HoloLens, which is the head device. Sadly, back then, we didn't have Aria glasses. So if not, our life would have been much easier. But you can see all of this is aligned. Everything has a ground truth with the Navis scanner. And basically, of course, we had to benchmark this. So we had to basically build from one of the devices, we built the map, and we localized the queries from the other. As you can see, each device in itself can localize well, but Spot in iOS, of course not. And this is basically because Spot and when, first of all, one is grayscale camera and looking below. The other one is colors camera and much more above. One triggers just one image, one has multiple. So if one image doesn't localize, well, it doesn't find the match. So we decided, of course, this had many parts of the pipeline. So we decided to check which one it was. And it is, as it seems, the retrieval, which basically by assuming a perfect overlap with the ground truth, you can actually see that it improves quite a lot. But in the end, still the viewpoint difference between Spot and the handheld devices is just too big. So the viewpoint is actually still a challenge. So the conclusions are cross-device localization has unexpected challenges. Matching and retrieval are still a problem. And there are basically other issues like, well, grayscale, global shutter, HoloLens and Spot cameras versus RGB rolling shutter iPhone camera. So all of these are challenges that as soon as you move to hardware, you have them. So I don't want to tell you too much about this because there is a workshop on this. So in case you want to attend to it, you can basically come and see our Crocodile in real life at 1 p.m. in room 301B. So overall, we fixed another problem, which is we can more or less align cross-device memory. But now this brings me just to my last part, which is can we upscale this and do knowledge transfer? Well, we have some challenges. Some of them you saw them. How can we make this to your home challenges? Well, perspective issues. Spot and you don't see the same. And of course, hand versus gripper. You have 5 fingers. He has 2. Well, we of course had to data record. So this is an overview of the data set. It's highly anonymized. So it's over 25 environments. We have 3D ground truth and panoramas. We have RGB depths video sequences. We have forces, touch sensors for each of the plus 235 articulated parts. So literally you have interactions now in multiple scenes. What type of interactions? Well, you have 7 different human interactions, 3 different grippers on a stick interactions, and then 1 to 2 robot interactions, because the robots were very sensible for this environment. So the viewpoints that we recorded are egocentric human perspective, of course, with Aria Gen 1. And then we have the egocentric wrist perspective, which I like to call the egocentric robot perspective, which is from the wrist, since the robot in our case doesn't have a head. And then the exocentric perspective. So what can we use this for? Imitation learning, VLAs, intent prediction, everything you can come up with, this data is going to be amazing for. So this is ongoing work, so stay tuned. And just to finish, get in touch if you want to do master's thesis, PhD, research day, just want to chat about any of the research, just feel free to let me know or talk to me in the hallway. And of course, this would have not been possible without this huge team of people. So yeah, and of course the heart of our team, which are robots. They all have also names. And yeah, thank you very much.
All right. Hi, everyone. It's a pleasure to be here today. As James has introduced me, my name is Björn. I'm in the final year of my PhD at ETH Zurich together with Professor Christian Holtz. And today I will talk about our research using the Project Aria glasses, which focuses mostly on seeing inside a person by estimating a person's heart rate, emotion, and personality. So ultimately what we try to achieve is to better understand a human's intention, what Richard also introduced this morning already. Most of you heard that the Aria Gen 2 glasses have now been introduced. And what we were most excited about to see was actually the health PPG sensor on the nose. And what this PPG sensor allows us to do is to measure a person's heart rate from the nose. And what we were initially so excited about is that Christian already started working on this like 10 years ago in a project lab Bella, where he attached different PPG sensors all over the glasses and was able to show that we can actually, when we record it from 3 different sites, on the face, that we can not only record blood volume pulse, but also, for example, blood pressure. So we recorded different kind of modalities from PPG sensors on the face. And now why do we think are these physiological signals so important for egocentric applications? On a lot of these large-scale data sets, such as EgoXO40 or Nymeria that exist nowadays, quite a lot of these tasks, such as pose estimation and ego-exo relation, they focus on a user's actions and motions and in the environment around the user. So they're mostly independent of a user's state. However, we argue that some of these tasks, such as, for example, proficiency estimation, they're actually influenced by the user's internal state, so the rich inner life of that person, which we kind of have to understand to be able to fully understand and solve these tasks. A person's internal state, which we also call affective state, is a pretty wide expression and includes not only the emotional state of a person, but it also includes their physiological conditions. So if someone is stressed, for example, or if somebody's in a mode of a focus. So it basically captures how people are feeling in the moment. And this, we argue, is quite important to add. I'll give you an example here. On the left side, you can see a person who is super relaxed, just browsing the web. And on the right side, you can see a person who's trying to make a deadline and is super stressed. Now, from the egocentric perspective, as you can see, now there is not much difference to see, right? You cannot really tell is that person stressed or not. And as a first step to basically help us detect such differences in a person's affective state, we started with a project called EgoPPG. And we define EgoPPG as a task of only having the eye tracking images, which you can see on the bottom right from the Project Aria Gen 1 glasses, then try to reconstruct the blood volume pulse, which you get from the nose PPG sensor, only from the video data. So as the blue, you can see our estimated blood volume pulse, and as the orange, you can see the ground truth from the nose PPG sensor. So there's no need for any additional sensors. And the main idea is quite simple. So we have an eye tracking image, and from the eye tracking image, we try to detect subtle changes in the color intensity, which happen when the blood flows into the skin. What makes this is inspired by something called RPPG. What makes this quite challenging now in these glasses is that we have a lot of natural eye movement, as you can see it out here, from blinking or when you look to the left or to the right. And additionally, as Aria glasses are worn by the user, when you walk upstairs, for example, or you shake your head rapidly, you get a lot of motion artifacts into these glasses. So to evaluate the feasibility of EgoPPG, we first designed our own data capture apparatus, where we used the eye tracking cameras from the Aria Gen 1 glasses. And then because the Gen 1 glasses didn't have a PPG sensor, we added our own onto the nosepad, very similar to the Aria Gen 2 glasses now. We then went on to record our own data set, which has a lot of everyday activities, such as, for example, the exercise bike to also have very high heart rates, but then also tasks which are reflected in large-scale data sets such as EgoXO40 and Nymeria, such as kitchen work and office work. So you can actually have a lot of natural activities that actually happen throughout the day. And then, of course, also walking upstairs. So to also get these kind of varieties in the natural motion. Overall, we recorded 25 participants with over 13 hours of recording, where we had a wide variety of different motion and also heart rate variation, which is important to evaluate how good our algorithm generalizes. So you can see our heart rate actually varies between 44 and 166 beats per minute. So it's quite a big variation between heart rates. To then estimate the heart rate from these eye tracking images, we developed a method called PulseFormer. So what it basically does, it takes the eye tracking images and the IMU from the Aria as an input, and then it uses a cross-attention algorithm to basically calculate which frames to put weight on and which frames to put less weight on based on the IMU. So when you have a lot of motion, you try to ignore these frames. You then put these frames into a 3D convolutional network, which is quite simple, and then what was quite important, what we found was adding these spatial attention layers between each of these convolutional layers. And what this allows us to do in the network to learn is to create these spatial attention maps, which you can see on the right. So blue means basically a value of 0, and 1 means it's yellow. So it basically learns to ignore the motion of the eyes, which cause a lot of motion artifacts, and just to use the skin around the eyes, which have a lot less motion. In the end, what we then obtain is an estimate of the blood volume pulse, which you can see on the right, from which we can then simply calculate the heart rate by doing a peak detection. Using this PulseFormer algorithm, what we obtain is a mean absolute error of 7.7 beats per minute across the whole 35 minutes per participant recordings, and a correlation of 0.85, which is quite high given that we have a high variety in motion and heart rate variation. Also speed-wise, what's quite nice is that this runs in real time. So we have almost 3K FPS on a GPU and almost 200 FPS on a normal laptop CPU. So it's definitely no problem to run these in real time, for example, on a laptop. Now, with the PPG sensor introduced in the Aria Gen 2 glasses, of course you might wonder, A, do we need to re-record all of those data that we actually already recorded? And B, what's actually the benefit of obtaining these heart rate estimations from basically eye tracking cameras? And we asked the same thing, and to evaluate that, we basically took the EgoXO40 data set, and we used our pre-trained model, which we trained on our own data set, and then predicted the continuous heart rate, which you can see here, for all of these 2,000 to 3,000 videos on the EgoXO40 data set. And we were then able to show the downstream benefit of these heart rate estimations by adding the heart rate to the proficiency estimation task and improving this task, the accuracy, by 14%. For those of you who are not familiar with it, the proficiency estimation task, what it basically does, it tries to estimate if a person is a beginner, intermediate, or expert in whatever they do. So it can be playing basketball, but it can also be, for example, somebody's cooking. And we can actually see that this heart rate information helps to determine a user's proficiency. And this validated to us that our method produced not just information that is nice to have, but it actually helps in the downstream task for egocentric vision tasks. If you're interested in more of this, I'll present this tomorrow at a poster session from 3 to 5 p.m. So feel free to come by or check out our project page if you have more questions. We'll also release the full data set and our model and the argumentations for all of these thousands of video from the EgoXO40 data set. So just go onto our website and everything is available now already. Now, estimating heart rate is comparably a simple task. The next step now is towards understanding a person's rich inner life is to actually understand and predict a person's emotions. Because emotions, they often align with task performance, success, and failure, so they have a lot of downstream tasks in our everyday life. And to represent emotions and personalities, there's different approaches that you can use. Some of the most commonly used are affect, discrete emotions, and personality. Affect is a continuous scale, so it simply rates as an emotion positive or negative, and how intense is that emotion. For the discrete emotions, we use the Michel's wheel, which basically defines 8 different emotions, such as fear and joy, like very profound emotions that everybody experiences. And that personality scale are from 1 to 5 for different attributes of your personality. To obtain these, there's quite standardized questionnaires from psychological research. This is just one example. So you basically, after each task that you do, give a score for each of these emotions, how you felt. We then designed a couple of interventions to basically elicit distinct emotions in participants during our study. And here I'll show you some examples. On the left side, you can see myself eating a jelly bean that tasted like rotten fish. And this was actually like really disgusting. And the intent was to get the emotion of disgust, which worked quite well. Then you can see a colleague who's telling jokes to the experimenter. And then a third participant who's playing Slender Man on a computer and is getting quite a lot of jump scares from playing this video game. So we could actually cause a lot of these emotions that we intended to cause. Overall, our study setup included the egocentric and eye-tracking videos from the Aria glasses, then these self-reports, which we got after each of these tasks from the participant. And then we also added quite a lot of physiological sensors, as related work has just shown that physiological sensors can help a lot to determine emotions. And we had PPG sensor, breathing rate, and ECG attached to the body, and also EDA, which for those of you who are not familiar with it, it simply measures how much you sweat. And sweat is a very strong indicator of how feared you are, your sympathetic arousal. You can imagine if you're stressed, usually your hands start to get really sweaty, and this is a sign of when your EDA increases. We then had in our study 2 different sessions, so session A and B, where in session A, participants were just watching videos which would trigger distinct emotions so that they didn't have any movements. It would be quite an easy setup. And in session B, they should do more naturalistic activities, which included playing games such as Jenga, telling jokes to the experimenter, but for example, also playing Flappy Bird, which makes you pretty angry if you play that. In total, we then obtained from 43 participants over 50 hours of recording, where we got in total 16 emotion ratings for the valence arousal dominance and the Michel's wheel of emotion. So after each of these tasks in each of these sessions, we obtained these ratings from the participants. The entire setup you can see here. So we had quite a lot of sensors attached, and this is important to remember. So as you can see, we had a breathing belt, the ECG belt, the EDA, all of these sensors attached, additionally to the egocentric glasses from the participants. And what we then did is we derived different features from these sensors. So from the Aria glasses, I'm not going to go into details too much here, but we got the pupil size, calculate some Fisher faces, the gaze, micro-expressions from the eyes, and also the motion magnitude, so how much you shake your head, for example, which can also give you a clue, for example, when you're scared. Also for the physiological sensors, we recorded over 100 different features, which were all backed up by related work, just to also have a background from the psychological research of what worked well for emotion prediction. And then finally, what we did is we used once the features from the egocentric glasses and the features from the physiological sensors and feed them together into a prediction model that then predicts affect, emotion, and personality of a person. And we kept this quite simple. So this prediction model here, there are only very simple random forest classifier, SVM classifiers, so that we can actually also evaluate which features are important for the prediction of our model. And our results then revealed quite some insights. So for the continuous effect, both the egocentric features and the physiological features were significantly better than chance. And they were pretty much on par, so they achieved similar performance. However, very importantly, for the discrete emotions, we saw that egocentric and physiological signals were both better than chance, but the egocentric glasses, all these modalities were actually quite a lot better than using these physiological sensors. And this is, we think, a very important and interesting finding because attaching all of these physiological sensors to the body is quite cumbersome. It takes a lot of time. You need to attach sensors to the skin of that person. Whereas the egocentric glasses, you just put them on and you can basically start recording or estimating a person's emotion, which makes it a lot easier. The personality did not work better than chance, but this is also kind of expected, as you can imagine from only 1 hour or 1.5 hours of recording, it's quite hard to estimate a person's personality. This project will appear in NeurIPS 2025 in December. We'll have the paper up in a couple of days, but we already have the data set and the code up. If you're interested, you can also check it out at our project site. At this point, also a big shout out to Matthias. He was one of our interns who I did this project together with. He did a great work in the data recording. So in summary, what we found is that you can actually monitor a person's cardiac activity only from the eye tracking cameras from the Project Aria glasses without the need of these actual sensors that you attach to the nose. And while for the emotion prediction, we found that we can predict better than chance the emotions, it's still a long way to go for emotion prediction and especially personality prediction from wearable devices. However, what is a really interesting finding is that for distinct emotion prediction, we can actually exceed using physiological sensors when only using the Project Aria glasses. And we think this can have quite a lot of implications in the downstream for like AR/VR interfaces, and also, of course, human-AI interactions. So if you can imagine the Meta Ray-Bans, for example, when you have an LLM talking to you, they can benefit quite a bit when they can actually estimate your emotions and what you feel, because they can better respond to your needs that you actually have that you cannot see from the outside. And then, of course, also health and well-being purposes. So you don't need to wear any wearables extra. You basically only need to wear your glasses, and you can already estimate your heart rate or also maybe your blood pressure in the future. Thank you very much for your attention. And if you're interested in the code data set and paper of all of these projects, feel free to scan the QR code. Everything should be up there. Thank you very much.
Thanks, James, for the warm introduction. And hi, everyone. So today I'm going to co-present with Michael from Meta. So I'm Bowen. I'm a research scientist from NVIDIA Research. So first, let me introduce our recent work, also presented in CVPR 2025, FoundationStereo, zero-shot stereo matching. So given a pair of stereo image, for example, nowadays you can capture with the Meta Aria glass. Later, Michael will also talk a bit on how they made the Aria glass capable of capturing the sufficient overlap between the stereo images. So the goal of the FoundationStereo is to produce a disparity or depth map without any fine-tuning on the target scenarios. So before we dive into more details, what is the value of a depth camera? So depth is a fundamental signal for 3D scene understanding. So whenever we talk about depth, we're not only talk about depth, but more about 3D spatial understanding. This can be helpful for like fusing to obtain 3D scene geometry and help estimating, for example, scene flow. It can also help to aid many other computer vision tasks like handling occlusions, object or body estimation or tracking, and performing segmentations. So there are also multiple ways of obtaining depth or 3D reconstruction. One popular way is the multi-view reconstruction, for example, core map or VGGT. One issue, though, is that usually for this multi-view capturing, they require you to offline capture multiple images with the surrounding views. And the issue is that for some applications, like embodied AI, we're usually dealing with a single perspective with the egocentric view, and we're also processing over a live camera stream, which is processing over online. And there are many dynamics. For example, when I'm manipulating my clothes or manipulating objects, I want how to live estimate these dynamic point clouds. Since the advent of stereo matching, we have come a long way. Traditional methods such as SGM can be applied out of the box because it doesn't need any machine learning. However, they are sensitive to common challenges in computer vision, such as textureless, reflectiveness, complex illuminations, and transparency. Such depth or point cloud causes issues for downstream tasks. Recently, deep learning-based stereo matching methods has made remarkable achievements. However, when applied in zero-shot setup, they are still far from being perfect, such as the bent walls, twisted tables, and shelves. The limited accuracy and generalization prevent practical deployment in novel scenarios. Today, with FoundationStereo, zero-shot and high-quality stereo matching becomes possible. Just applying it out of the box, it produces clean and sharp metric scale depth. In the lifted point cloud, flat table, nicely curved robotic arm, straight walls with perpendicular corners are all faithfully recovered. So to this end, we revisit the problem of stereo matching by approaching the topic in 3 different angles. First, let me introduce how we scaled up the training data with high-fidelity simulation. Specifically, we created a set of high-quality realistic scenarios in 3D, designed by artists. Each scenario model consists of semantically meaningful layouts and floor plans. We also designed a smart camera spawning strategy by taking into account the attributes of the floor plan. We additionally insert diverse 3D object assets into the background to compose the entire scenes. In total, for the FoundationStereo dataset, it features high-fidelity scene layouts and rendering produced on 48 A40 GPUs for 10 days. It also covers large-scale and rich diversity populated by various 3D object assets and the backgrounds. We also randomize the camera intrinsics and baselines, so later when the network trains on such dataset, it can be applied out of the box on many different stereo setups. Next, I will introduce how we injected the monocular parallels given the recent exciting advancements in monocular depth estimation. We inject the latent features from depth editing V2, which has been trained on large-scale internet data. A side-tuning CNN adapts the frozen features to our stereo setup. Here shows an image pair with different lighting condition, which could have been ear-posed for standard stereo matching. We found the rich monocular parallel significantly enhances the reliability on regions such as the lamp and the guitar hole. Lastly, we advanced the architecture design to make effective use of large-scale training data. Once we extracted the features and build a coarser volume, in addition to CNN-based hourglass, we add another transformer branch. We downscale the coarser volume and reshape into disparity tokens, followed by a series of transformer encoders. This disparity transformer module further enhances long-range context reasoning along the epipolar line. For example, on these repetitive textures for the fences. Flash attention is also leveraged for memory and speed efficiency. So once we apply this disparity transformer, we can clearly see the depth has been obtained much more sharply on the repetitive texture, on the repetitive fences. Now let's take a look at the results. Here shows the qualitative comparison. All methods are run in zero-shot. Comparison methods are challenged by the reflective floor, translucent microwave, and black holes in the trash can. Ours is the only one that reliably predicts these regions. The difference is more significant when visualizing the point cloud. Methods including Croco V2, Stereo, and IGAP fail to identify the ground plane. Zooming in, the microwave inset within the dark cabinet, as well as the reflective griller, introduce challenges. Moreover, the ceiling and the floor are perfectly straight in our point cloud. The turning corner with vertical wall is sharply visible. Here's a restroom scene, including transparent cleanser bottle and large textureless regions. Nevertheless, FoundationStereo produces perpendicular point cloud around the corner and a nice curvature around the white toilet. We also compare to the state-of-the-art monocular metric depth estimation methods, such as depth anything V2, metric version, and the depth pro. We lift all methods depth into 3D point cloud and align in the same coordinate space for comparison of their scales and the quality. Thanks to the stereo setup, FoundationStereo produces the exact metric scale for the targeted scene, as other molecular depth shows some shearing effects around the wall corners. Here's a video showing the relative depth quality on the local surfaces. First, it presents the depth 19 V2 and the depth pro. The shiny tab presents challenges, whereas ours produces straight ones. Zooming in, depth 19 V2 has issues differentiating between the depth of the hand and the background sink. Depth Pro has slightly better results, but still kind of noisy. Ours produces a clean and straight hand point cloud. We are proud that FoundationStereo has enhanced the various downstream tasks, such as object scanning, large-scale 3D mapping, robotic grasping, and manipulation. To conclude, nowadays, zero-shot stereo matching is finally beginning to work. Depth sensing now relies less on the hardware. In the past, they usually depends on the involvement of LiDAR, structured light, or time of flight. Today, we're now able to advance with the advancements of the software, like the algorithm and the internet data. And what's even better is that 3D data is now becoming easier to capture with the Meta Aria glass. With that, I will hand over to Michael.
Start this here, yeah. So Bowen talked about the generic sort of like FoundationStereo that runs out of the box. My talk will actually then explain how we can take this and apply it to data that we can capture with Aria Gen 2. And this is the example that we've shown previously. This is just running FoundationStereo on data that's part of our pilot data set. Now, there's 3 items I want to talk about. The first one is the hardware, the cameras. And with the new design that we have for the Generation 2 glasses, we actually added 2 more computer vision cameras. In particular, there's a front-facing stereo pair. These cameras have a resolution of 512 square pixels, a global shutter, and they're tightly synced so that we actually take pictures at the same time. Most importantly, there's significant overlap. It's about 80 degrees of overlap between the 2 cameras that are front-facing, and that's actually forming the stereo pair that we use for FoundationStereo. Now, the second part is stereo rectification. And if you're sort of like in the community, you know that rectification transforms epipolar curves to straight lines that are scanline aligned, which makes your reconstruction typically more efficient. And essentially, it turns stereo matching into a scanline aligned correspondence search. But more important in this case, rectification actually normalizes out any camera-specific and time-varying projection geometry. Time-varying because, the glasses may bend. And this is actually what allows us to use the foundation models that are pre-trained without specific adaptations to the data that we have from Aria glasses. And then we can use the data from the rectification to also map it back to depth, and then finally go back to 3D world space data. Overall, this is the full pipeline that we run. We take the images from the left and right CV cameras, we rectify them, run FoundationStereo, and then we get a disparity image out. This image is then converted back to depth, and then finally we can convert this to a world space depth map or a 3D point cloud. The 2 yellow boxes that are in here actually take data or represent data that we collect on the device, which is the online calibration, which updates the intrinsic and extrinsic camera parameters, as well as the camera pose that comes out of the VIO system. So here's an example of what this means. On the left side, you see a camera stream from the computer vision camera. On the right side, you see the per pixel disparity rendered as somebody is cleaning up their house. And you can see sort of like the quality of all the depth that we get with that. In fact, talking about quality, this is just taking the raw data from the FoundationStereo, taking also like the poses we get from Aria, and then just integrate this in a sign distance function-based fusion approach. What you can see is like for all the objects that are in there, it's actually giving us a really good and consistent depth. We see some artifacts in sort of like planar surfaces that don't have texture, and these show up in there, but overall, it's really a very good model and result that we get. So finally, how can we actually make this run fast? Because if you run this out of the box on the GPU, and this is a A6000 that we use for testing, it takes about half a second to run per frame to get the depth out. Now, we took a series of steps. One of them is like exporting this, and then changing a couple of the parameters. For example, we're running this on 16-bit floating point instead of 32-bit. We turn off dynamic batching. In this case, we also reduced the size of the images by a factor of 2, making them half resolution. And then finally also put the stereo rectification on the GPU. With that, we end up with a system that runs with 23 frames per second on this A6000 GPU. But GPUs have evolved. And if you take a modern system like the top of the line that you can get now, which is the 5090, we're actually at 80 frames per second on 256 square resolution, and we can run 20 frames per second on the full resolution data from the cameras. So with that, let me wrap up and saying sort of like Aria Gen 2 stereo, it's really a game changer because it virtually adds a depth camera to your glasses without us ever putting any specific hardware on it that is depth. We pre-computed all of that also like for the Aria Gen 2 pilot data set. So if you're interested, you can directly download that data set and look at the quality that's there. Looking forward, you know, there is room for optimizations. For example, fine-tuning models for the specific cameras we have, improving temporal coherence so that there's less flicker, optimizing the inference, and also like distilling it in even smaller models so that you can overall hopefully get this even faster. And with that, I'd like to conclude the talk part and actually want to say we're going to have a live demo now, if everything works. So this is the fingers crossed moment. And we will have a live demo of this system also at the Meta booth in the exhibition. So with that, let's switch over. All right, can you hit V, please? Yeah. All right. So this is essentially on the bottom left, you see on the left the stereo, the disparity map, on the right, that's the normals. And then sort of like, can you hit V once, or and select that V button essentially. So essentially you see it's a depth map. If I get somebody who comes close maybe to just like show someone, just see here, here's my hand rendered in 3D or so. So you can actually see that it's really working well and it's really running also in real time here. Right, somewhere back there. Yeah, can we get a V once more, please? So this is just the, yeah. All right, just so that you believe, this is now a rendering of the point cloud. Previously, we showed you the triangulated depth map. So just to show that as well. Yeah, I can rotating it with respect to the camera here would require us to maybe unclick that V button. Yeah, so now we're actually moving the camera freely, or actually the camera is fixed and I'm moving the glasses freely. We're getting lost in 3D through here. All right. And then we can try, if we can, to also switch to the color images, if you can get the texture in there. Let's see. Color map or color? Color. Yeah. So now we have actually, it's very dark in this room, but essentially, if we add more light, it's getting it a bit. Let's just see. Yeah. It's a trade-off. It's a trade-off between that's in there. So I think so. Like with that, let's maybe end it here. You can try it yourself at the booth, and then thank you very much.
Okay, hi everyone. So thank you for the introduction. And today I will be talking to you about egocentric video understanding in operating rooms and kind of the challenges that come with that and the opportunities that we might get from this. But first I want to start with a bit of motivation for this. And I brought a video from Grey's Anatomy, but it will be a bit graphic. So if you're not, if you cannot see blood, then this is your warning. We don't get sound, so I'm going to do something like this.
Yeah, I think. Oh, there it is. Holy moly. Holy moly. Wow. It's been so long since I've seen a waterfall in person. This is just the best. Yeah, I'm going to stay here a while, you guys.
Turn that off. I need to know what happened now.
Me too. And and the question and kind of what this talk is going to be about is in this really, really kind of high stakes environment, how can we kind of understand this environment with AI? And essentially, the question here is, what if we could have an AI system that can automatically detect mistakes, predict the next steps, or in general help surgical staff better? And in a long-term vision, what if we could even replace surgeons with robots entirely? I think everybody here has seen science fiction movies where there's some autodoc just like fixing you up. And maybe we can take a couple first steps in this direction. But for that, we need data, right? And there's no data, and there's real challenges to getting this data. Because there's a lot of like hard challenges to overcome here. First, there's ethical considerations. So these are really life and death situations. And these really sensible situations, the question is how can we actually record these in a dignified way? Because there's like actual people's lives at stake here. And really, we want to make sure that we can record this in a way that is like okay for everyone. Another question is even, can we make such data public? I won't answer these questions in this talk, but maybe in the future we will. And also there's privacy issues, like of course the patients themselves, but what we heard from talking with doctors is very much that they don't like to be recorded as well, especially what they're saying, because they talk just randomly during the surgery about their everyday lives and gossip about hospital stuff, like Grey's Anatomy, yes. And of course, they don't want to have that recorded. So these are some of the practical challenges, but there's also safety challenges here. So the question here is, does recording with egocentric devices actually impact surgeon performance? Like if you're wearing these glasses, does it decrease your performance? Usually if you're cooking something, this is really not that important. But if you're cutting somebody's brain, maybe you want to think about this. There's also sterility aspects. So these have to be sterile. And can we actually do this? Also, there's other things like FDA classification that you have to think about. But from looking at it, probably these would fall under like recording devices, but it's a bit unclear because they're wearables. So what we did in the following slides is we just simulate surgery for the beginning, just to get some data to get started. And with that, I would like to talk about EgoXOR, which is upcoming at NeurIPS from my colleague Engel. And this is kind of a play on words, of course, on EgoXO4D. And let me explain why this is. So in our chair, we have a collaboration with the University Hospital, and they have a training room where they do EMT first responder trainings. And in this kind of simulated OR, we can set up and we can record some data. And how we did this is that we have, as you can see on the top right, like these two are kind of Kinect RGBD cameras mounted to the ceiling. And in this work, for the first time, like these are the exos, we also bring the egocentric view into this, where we have multiple people wearing Aria glasses, recording simulated procedures, and we also put one Aria glass on this like surgical light, just to have one more viewpoint. Cape is your friend. And yeah, this is kind of the overview of this visualized. We also have a live ultrasound feed here that we stream and we also record from this. And this builds on the work that we presented at CVPR. This is an example of this RGBD reconstruction that is captured from these Azure Connect cameras. So these are kind of time synchronized, and you get this RGBD, like very coarse RGBD understanding of the scene. But what we do now here in EgoXOR is that we bring also the egocentric understanding here, also with audio.
All right.
Needle
has been placed.
And
Will be done right away.
is done. I think the syringe is jammed.
And maybe this was a good example of kind of the things that we can do here. Before I start, you can see all the different viewpoints of the surgical staff, pretend surgical staff, the patient sometimes, and the rest of the OR here.
I'm going to do the first incision now. And nurse, I think there's something, microscope seems to be
Let me check out, try to recalibrate.
Cool.
Okay,
I'm going to do the first incision now. And nurse, I think there's something, the microscope seems to be a little bit misaligned.
Let me check out, try to recalibrate.
So these have kind of all the standard machine perception services annotations. So we get these coarse hand poses, we get eye gaze, and we also get the camera trajectories for all the Aria glasses wearers. We also synchronized all these together. This was a bit of not straightforward with the Gen 1s. I heard this is going to be much better with Gen 2, so looking forward to that. But yeah, all these videos are synchronized together with eye gaze. And of course, we also get the SFM reconstruction here. I think you've seen a lot of this, and if you're interested in this, probably you know about this. But I'm just going to let it play a little bit. And this is one example of the RGBD we get in addition to the egocentric views that we have. And what we can also do is try to register all of these in the same coordinate system. We haven't done so far because this turned out a bit tricky. But in the end, all of these live in the same coordinate system. So we can also align the sparse point cloud that we get with this more denser one in the end. And to give a bit of an overview of the overall data set that we captured, you've seen all the different modalities that we have. In total, we have 94 minutes of procedures divided into clips of actions that we're doing and performing. And the procedures that we simulated here are ultrasound-guided needle insertion, where we also have the ultrasound machine and can simulate this procedure. And the other one is with a surgical microscope, where we have minimally invasive spine surgery. Both of these procedures include workflow deviations and mistakes, so we can make this a bit more realistic and also have something to optimize against, so we can detect these things. In total, we have around 85,000 annotated time steps, and we annotated this data set with semantic scene graphs, in addition to all of the data that we get from the Arias in general and the RGBD. But now that you learned about the data itself, we also have to talk about, okay, how do we actually understand this, right? And the method that we developed for the beginning for this is to predict these scene graphs. So you can see an example of these scene graphs at the bottom here. So how they're defined is usually as a triplet. So we have, for example, the head surgeon is currently scanning a vertebrae. And this is the annotations that we provided for this data set. And it's like annotated for 85,000 time points in this manner. And of course, in the top, you can see all of the inputs that we can use for a model to predict these scene graphs in the end. Exactly, just statistic overview and a bit more example here. So most of these classes are close to lying on and not really that semantically meaningful except in a spatial sense. But this is also, of course, important to understand what is going on in a scene. The more long-tail distributions, of course, are a bit harder to predict, but this is pretty standard. The model that we're using for this is an extension of the CVPR model that we had. So essentially, the bottom you can consider as the CVPR plus ultrasound. And we essentially encode all the different modalities, we pool them together, project them, and then concatenate them and feed them into a large vision language model, which then is fine-tuned to predict these scene graph triplets. The interesting part is that for the egocentric data, now we can introduce another additional branch that can use the egocentric RGB video, the hand tracking, and the eye gaze. And what we show here is that using this additional data is actually improving the results, like in F1 score for predicting these scene graphs, by quite a lot. And what's even more interesting is maybe the table at the bottom, which in the Neuros paper was hidden in the supplementary, is that if we're using ego only, we actually get quite a bit improvement to using the outside views. And this kind of shows that the egocentric view is really important to understand what the surgical staff is doing. If you have these outside cameras, they're good, but if you augment them with the egocentric view, which is much closer to the scene of action that you're currently doing, this gives you a much improved performance of understanding what is going on. So this is kind of the preview of this paper, and maybe to give a bit of an outlook, this is still very early work. So this is all simulated, and this is not real surgeries. We try to model this as close as possible to real surgeries, but of course there's no blood, there's no cutting. So to model these, you have to actually record real data. Another thing is that these semantic scene graphs can be used for downstream tasks like workflow anomaly detection, like unexplainability. They're really nice to look at, and like medical staff really like to have something to look at, but they're not 3D yet. So if we had 3D scene graphs, this would also make reasoning about the scene spatially a bit more interesting. And then, of course, as I said in the beginning, it's pretty difficult to move to real procedures based on all of these challenges that we're facing. But I think we will at least explore this direction further because there's a lot of things to gain there. And maybe a bit of the opportunities to bring this back to something that might realistically happen at some point. I think we will hear a bit more about vision language action in the next talk. But these models have shown a really great promise to generalize robotics, but they need a lot of data. And if we want to go at some point into fully automated robotic surgery, then we need this data. And this was kind of the first step in this direction. And with that, I would like to thank all of these people here, which you can see on the slides. You can also take a look at the data set itself. It's hosted on Hugging Face. And yeah, this was a joint work of Engel and Arda. Arda is a master's student, and he's still, I think, looking for a PhD position. So if you have something, let me know. And with that, I conclude, and thank you very much.
My name is Danfei. Thanks you all being here. The goal of my talk today is to convince you that the future of robot learning will be driven by human data, and that Project Aria glasses is an excellent research vehicle for this problem. What motivates our work largely is that most AI systems we see today are driven by human knowledge, and at this point, a large part of human knowledge is captured by the internet. And this knowledge in turn gets downloaded, cleaned, and absorbed by these gigantic foundation model we see today. For the past few years, robotics community has rediscovered teleoperation as a powerful tool for transfer sensory motor knowledge from human to robots. And we've seen a lot of successes in both academia and industry. A lot of really impressive demos on tasks we thought were previously impossible for robots to do. So for those of you who are not familiar with this topic, because I'm in the Vision conference, let me first explain what teleoperation is and why that's useful. Was the work Jay and I did back in 2020. When a human operates robots with a control device such as iPhone here, we capture two streams of data, what the robot sees and the corresponding action. This creates a direct mapping between perception and action in the policy model, essentially teaching the robot how to to react to different situations without explicitly writing down the rules, which is very, very, very different from how people used to program robots. An important point here is that we're not just transferring abstract semantic knowledge, but rather by perceiving and acting through the robot's body, we are transferring sensory motor knowledge that's largely missing from today's internet data. But teleoperation creates a very, very tight bottleneck in a knowledge transfer pipeline. For those of you who have done teleoperation, you know that it requires pretty unnatural and intentional effort from the operator. And of course, having to bring the robot around for wherever you want to collect the data with. So that's very, very inconvenient, not scalable. And argue that it is unlikely for us to scale to the to reach the data scale of other domains like computer vision or language if we rely on teleoperation alone. So the central piece of question our work is really answers the question, how do we transfer sensory motor knowledge from human to robot at scale? And our research pitch is to instead learn from human experience data. And this data will be collected from human without no robots involved and contains sensory motor information essential for robot policy learning and can be captured without intentional efforts from the humans. And so with that, I like to basically tell you through a line of work that we've done, a subset of them, and try to convince you that these are really interesting research directions, and I'll tell you some open questions that's on top of my mind. So the first research landmark or milestone was ego mimic, scaling robot learning via egocentric video. And this core project is to capture embody human data from egocentric view with wearable devices, which means that we can collect this data anywhere. And unlike third-person videos from internet, egocentric data captures how we as people perceive the world at eye level. And specifically, we use Project Aria glasses to capture these data, which we all familiar with, and these contain essential information for decision making, such as hand tracking and images and head localization. And our work is about turning these raw data streams into human data that can be treated as equals with human data, with robot data. So we want to view them as basically two embodiments on a spectrum that on one end, we have humans, and on the rest of the spectrum, we have different kinds of robots. And we achieve this by bridging sensing, action, and kinematic gaps, and develop joint policy learning architectures that can scale primarily with human data. Let's first talk about how to align embodiment viewpoints between human and robots. For embodiments, we discovered that to learn from human data, we actually need a human-like robots. And we didn't really have too much options back then, so we actually had to build our own lightweight robots, which are basically two 6-off arms. And one very important decision we made was to actually mount a Project Aria glasses on a robot so that it matched in viewpoint as an average adult. And for those of you who have worked with I'm sure most of you work with cameras. Camera gaps are very important. Any gaps in camera lenses and exposure could create gaps in your models, downstream problems. So we actually use the exact same cameras for both human robots to bridge this gap. Among the many problems we had to deal with to learn from egocentric data, I want to highlight one very important challenge or interesting challenge, which is that our head moves and a robot's camera typically don't. When working with robots like ours, the robot's grip movements is referenced relative to a fixed camera frame and can easily get action trajectories into in a fixed coordinate frame. But with egocentric human data, like the ones I just showed you, our head naturally moves as we work. We look around, move to different workspaces, and focus on different aspects of tasks. This means that hand positions track with a relative to a moving camera frame. And we need to stabilize this reference frame to make human hands tracking data usable for robot learning. And luckily, Aria gives us really good hand device tracking via SLAM, which will be the key to our solution. So very kind of briefly, our solution is to transform future hand positions into a current camera frame. Here we show hands in the moving head frame, right? You have a camera, the Aria glasses tracking hands at different camera frames. But if you project it back through this VIO of the camera, you can actually create a very smooth hand trajectories. Looks like this. So this is basic, we got this by projecting future hand pose back to the current camera frame. So you see these smooth trajectories. With a line observation action space, we were able to design very, very simple architecture that co-trains from both human robot data, and almost all of the network weights are shared among human robots. So we showed that this architecture was able to learn a shared representation that scaled policy performance primarily with human data. So won't go into too much details of architecture. So if you're interested, talk to me or read a paper. We tested robots on a variety of tasks, including the grocery task, where a robot must pick a grocery bag with a thin handle and pack all the chips inside. And bags are slippery, so we'll also have to kind of react to these kind of mistakes. And laundry tasks for basically folding small shirts with different colors. And of course, we all need robots to do our pullover coffee. So our student trained the robots to do exactly that. I'll let the robot do that. Drinking water. Yeah, so, and then this robot's also able to react to different kind of situation like real-time planning or swapping kind of different kinds of balls, different colors. And finally, we can actually move the camera or the robot around because we train on so many diverse viewpoints from human data. It's actually pretty robust to viewpoint changes. So the main question we still want to answer is, does Egonomics scale with human data, right? What we want to kind of break from the shackle of teleoperation data to use human data. And here, the x-axis is our data, our time you spend on collecting data, either human or robot data, and the y-axis is the task performance score. And you can see that if you only train on robot teleoperation data, you have this moderate kind of scaling curve where more data, better performance. But with 1 extra hour of human data, you actually have a gigantic jump in performance. This is mainly because we can demonstrate a task really, really quickly, up to 10 times as fast as teleoperation with our hands. So, and also you don't need robots around, so you can collect data anywhere, which creates a massive advantage for scaling robots with human data, robot performance with human data. We also brought our robots outside to a variety part of campus. We didn't really collect new data on these new scenarios, but this kind of works. So one of my favorite examples is on the lower right, where the student kept tossing on new chip bags to the robots. And then, I mean, it kind of does what it's supposed to do. It eventually fails, but it really shows the robustness of our policy trained from human data. Okay, so one other thing I want to highlight is that we want to go beyond egocentric vision and tabletop manipulation, which is pretty much the standard setup for robot learning today, towards looking beyond like vision, towards tactile and potentially full body motion. And one work I want to highlight is from a past project in Coral, where we try to learn from tactile data, where we directly strap a tactile sensor on the person's fingers and basically use that to collect tactile human data and use a camera to track the position of the fingers or the sensors. And we didn't use Project Aria glasses for this project specifically, but we could easily swap out these devices for tracking hands. But because Aria doesn't measure tactile, so we do have to instrument this to collect the tactile data. And we showed that we were able to actually train policies directly from these data to transfer this to robots. And one thing that we noticed here is that direct imitation learning doesn't actually work for these kind of complex tasks, so we had to do some RL fine-tuning online. But but the policy trained from human data was able to largely complete tasks. So there was a lot of somewhat quickly to fine-tune this policy to perform well on these tasks. I will show that the policy works on a variety of perturbations, such as new materials, new shapes of that peg, and new tasks like screwing things on a hole. So these are all achieved via fine-tuning the same base policy. Okay, finally, I want my personal favorite topic is to go beyond tabletop manipulation towards mobile manipulation. Many of you probably have seen this video called Mobile Aloha. It's a work called Mobile Aloha. It's very, very impressive, which is also partially responsible for driving all the craze around robotics today. But as you notice, it's painfully slow to collect this data, and you also have to kind of have the robot around. You can see the lower left side is 10x speed up video. So you don't want to do that, be the person who to collect the data with this kind of robots. On the other hand, human data is almost trivial to collect, as I explained earlier, and we naturally move around in our space to do all sorts of mobile manipulation. And one very, very important thing is that modern wearable devices capture more than just videos, right? We actually have the full body motion captured with our hands in a very accurate global coordinate system, along with the disseminated point cloud. This is specifically captured by Project Aria, which you can see that it more or less captures the full body motion of human. And we do think it's possible to learn full body manipulation from this kind of data. So the question that we want to answer in this work called Emma is really that. I'll wait for him to take the picture. All right, is Emma, the question is, can we scale mobile manipulation with human data? This is done by our student, Lawrence Zhu. The answer is that yes, but we still need to borrow a little bit of robot data. But here, we don't actually need to move the robot around. It's just static robot data combined with massive amount of mobile human data that allows us to train mobile manipulation policies. And architecture-wise, it's actually quite simple. So it's exactly the same as we done before. Massive transformers train on all sorts of different data, including both human robots, shared weights among human robots models. And one thing that we did here was that we actually have this different decoder heads, end effector, upper body motion versus navigation heads. And we have the phase switch prediction that switches between manipulation and mobile. I would love to explain more about why this is necessary and why still learning truly full body manipulation, like moving while manipulation, is such a hard problem. We have some ongoing work on that, but I'll skip the details here. And in terms of system, we just basically put a differential drive robot on the bottom of this robot, or same robot, so it's able to do the task. We also had to do some retargeting, but I'm going to ignore, glance over the details here. So does it work? We showed that it works on a few very challenging problems, such as serving breads or serving croissant here to a different table. And one very interesting task is this serving. We compare with Mobile Aloha, and we'll show that our method performs better. And the typical failure cases of Mobile Aloha is that it just runs off and run into things. So clearly bad. One very interesting task we did was hand over wine glasses to a person. And this way we actually stress test the generalization of, because the person can be anywhere. So it learns to navigate the person just from the human data side of this. And because it only relies on human data for navigation part, we can actually collect data on a new complete new scene and combine with the existing static robot data to train a robot to complete the same task in a completely new scene. So we don't have to really collect any more teleopera data if your robot is able to handle this kind of varieties. And finally, we have this cool task where we want a robot to do grocery shopping, so it's able to do this kind of by-manual manipulation and coordinated pick up this shopping bag and move the shopping bag to the other table to hand over to a person. Okay, so quantitatively, we show that for this long horizon task, if you look at the per stage success rate, Mobile Aloha the success rate kind of dies off later because it's just it's the more progress towards the end, the harder the task is. But our model is able to still achieve 50% success rate for the entire task, which is quite impressive. And very exciting thing that we discovered is that with the scaling trend still holds, and I'm very confident about the scaling curve where x-axis is the amount of human data, y-axis is success rate, because we did 50 rollout per point on mobile manipulation. That was a long time. So it took us like a few days to run these experiments. So I'm very certain that this is the case. So these are the technical works, kind of glance of the technical works we've done in this area. We have a few other papers. If you're interested, check out our website. But I want to kind of talk you through some open questions that on my mind that maybe give you a flavor about kind of where the robotics community might be going next especially with learning from human data. So I grouped them into three categories: hardware systems, data algorithms, and research community. So for hardware systems, the question I want to answer, the most important question is, how do we capture human experience and context? And the claim here is that first-person video is not your sensory motor experience, is also not your decision-making context. So they're all different things. Like what I mentioned before, our experience is more than just egocentric vision. Beyond the current egocentric vision devices, we're hoping to see more advanced and portable sensors for example, for tactile. And a good example is the Gen 2 device just presented that's able to capture other sensor modalities like audios and heart rate, right? But the things are obviously still lacking from the tactile side. We have tactile gloves and more recently commercializable EMG wristbands, but things are still quite in flux there. And the context for necessary for making decisions is also more than your instantaneous observation, right? So if you look at this third-person video, the reason that the chef turns around to look at different counters and get the ingredients from one counter pouring to the pot is because they remember that the fact that they prepared the ingredients a few minutes ago, and through years of training, right, they know how to adjust the heat appropriately to kind of to cook a good dish. And this is all more than just your instantaneous observation. And how we assimilate this kind of context knowledge into policy models is still very much an open question. On the side of data algorithm, it's arguable, I will argue with you, if you don't agree with me, that human embodiment is the most universal and is most scalable data sources. And the more human-like the robots are, this will make human data more useful for robot learning. And if the results I just present continue to hold at scale, it will make sense to have this kind of setup where you have massive amount of human data with small amount of embodiment-specific data. But the open question really is that what roles should these data play, right? Like, how do we actually use them to train these large robot policy models? And I have some speculations. So for example, there was a data pyramid picture that my friend and colleague at NVIDIA, Yuko Xu, presented a while ago, now became famous, that from human data perspective, you have a massive amount of human data as a foundation for training the policy, and you fine-tune that with robot data. But I would argue that it's just as likely that we'll have this kind of inverted pyramid where the robot data is the foundation for being able to learn from human data, because you can argue that by learning through by learning these basic capabilities that pick and place and insert, you are only then you could actually properly make use of human data. So I'm not advocating for either picture. Both of them are equally likely to me. So we're seeing evidences for both pictures, but I do want to point these out here, and I want more exploration from both sides. And finally, I want to talk a bit about how to drive collective progress as a research community. For robot learning, we have made tremendous progress by coming together, build data sets like OpenX embodiment and Droid. And for egocentric data, we have prior successes from Ego 4D application and more recently Ego Dex that's more focused on the manipulation data. But if we had to learn anything from past few years of robot learning, data-driven robotics, is that large data set alone is not won't solve the problem. We need a continuous cycle of data to algorithms to evaluation, especially on robot evaluation, which helpfully tells us what data is more useful so that we can collect more of that. At the same time, there's a unique opportunity here to build a community in that we can at least agree on a single embodiment as a data source. So along with a few academic groups and industrial partners, we're currently developing some standard infrastructure for this whole cycle. And the hope is that this would potentially enable the community to make things more comparable and accumulate more and more insights and useful data along the way. And I'm hoping to be able to share that in the next few months, so stay tuned. And with that, I'd like to conclude talk, and here's the works I mentioned. Here's the main contributor for these works, and here are my sponsors. And thank you.